Let's take a journey into the past. So far back, it will make the age of dinosaurs seem like yesterday. We'll travel to a time before even the mighty supercontinent Pangea, whose outlines many of us vaguely remember from school geography lessons. But before we delve into these ancient lost worlds, let me ask you one question to set the right mood. From what corner of our modern planet are you watching this video? So let's start with something more or less familiar. Pangea. When we hear this name, we imagine a single colossal landmass. It's a gigantic geological puzzle where all the modern continents fit together perfectly. You've probably seen those maps where South America sits snugly next to Africa, like two jigsaw pieces that fit together perfectly. Perhaps you imagine the vast expanse of Pangea as the stage where the drama of the age of dinosaurs unfolded, before titanic forces tore this world apart, sending the continents on their long journey. And all of this is absolutely true. Pangea really did exist. This supercontinent formed approximately 300 million years ago and stretched from one pole to the other, changing the climate and life on the planet. But here's a fact that often escapes attention. Pangea was not a unique phenomenon. It was not the first time Earth had assembled its lands into a single whole. Far from it. Pangea was merely the latest in a long series of titanic mergers. You see, our planet is a living, breathing organism in perpetual motion and constantly reshaping itself. Tectonic plates slide and collide, ocean basins are born and die, mountain ranges rise to the skies only to be eroded into dust by winds and rains, and over hundreds of millions of years, continents inexorably converged, merging into a single supercontinent, then breaking apart and beginning their slow dance of convergence again. This great cycle has repeated itself over and over again in Earth's history. If Pangea was the final chapter of this saga, what worlds existed before it? What landscapes lay across Earth long before the dinosaurs appeared, before the planet was blanketed by the first forests, and even before the first complex organisms dared to venture onto the lifeless land? To answer this question, we must stretch the boundaries of our imagination. The timescales involved are truly colossal. Hundreds of millions of years seem like an eternity to us, but for the planet's geological history, they are just a few pages in a vast book. If we compressed all 4.5 billion years of Earth's history into a single 24 hours, Pangea would appear on that timeline only a few minutes before midnight. Yet before those final moments, entire worlds existed, born, flourished, and perished. We are presented with images of oceans covering almost the entire planet, and continents drifting and colliding along trajectories we can only barely reconstruct today. And here's where the hard part begins. The deeper we delve into the geological past, the less direct evidence we have. Ancient rocks are eroded away, remelted in the planet's depths, and with them, fossils, invaluable witnesses to bygone eras. Much of our knowledge of pre-Pangean Earth is based not on hard evidence, but on hints and clues, subtle magnetic signatures frozen in crystals, and chemical imprints hidden in the oldest minerals. Putting this picture together is like trying to solve a jigsaw puzzle with only a handful of pieces remaining. The image on the box long since faded, but piece by piece, scientists have been able to reconstruct enough fragments for us to imagine these forgotten worlds. One of them is the supercontinent Rodinia, which existed about 1.1 billion years ago. Even earlier was Nuna, also known as Columbia, a gigantic landmass more than 1.5 billion years old. And before that, there was Kenorland, perhaps one of the first truly large continents, tiny compared to its descendants, but colossal for its era. These names, Rodinia, Nuna, Kenorland, sound like the names of lost kingdoms from a science fiction novel. But they are real milestones in the history of our planet. During the time of Pangea, Earth was already covered in rustling forests. Deep rivers flowed, and reptiles and insects inhabited the land. But fast forward to the time of Rodinia, and we see a world without a single tree, a single land animal, or a single flower. It was practically an alien planet, and if we look even further back, To the eras of Nuna and Kenorland, life was represented only by primitive microorganisms clinging to coastal rocks or swimming in the warm waters of ancient seas. To imagine Earth before Pangea is to imagine a world where the main actors were the continents themselves, drifting and colliding across a virtually empty stage. And although life was simple back then, the geological drama played out on a truly grand scale. Volcanic eruptions that could last millions of years, glaciers that froze the planet from pole to pole, and oceans that submerged entire continents. Each continental collision changed not only the map of the world, but also the composition of the atmosphere, the chemistry of the oceans, and, ultimately, the course of evolution itself. Sometimes, when we think about history, we imagine humans or dinosaurs, and it seems like an incredibly distant past. But the deep history of the Earth extends immeasurably further. The entire history of humanity is but a brief moment compared to these geological supercycles. Even the dinosaurs who reigned on the planet for 165 million years appeared and disappeared after not a trace remained of the supercontinent Rodinia. It makes us wonder what that ancient Earth was like. What did the sky look like without birds? What did the air smell like without the scent of flowers? What was the silence like in a world without the buzz of insects or the cries of animals? We will never know for sure, but we can gather enough fragments to try to imagine it. So, as we journey through the landscapes that existed before Pangea today, remember, Earth was never static. It was always living, breathing, changing, and rebuilding itself. This is not just the story of rocks and tectonic plates. It is the story of the planet itself, which had many faces, some vaguely familiar, others utterly alien, long before we came along to name its lost worlds. When most of us first encounter Earth history in school, the idea of Pangea seems like a startling concept. The teacher moves the continents around on the map, and suddenly South America fits perfectly into the curve of Africa. North America converges with Europe, and India presses against Asia. It all seems so logical, almost too perfect to be true. The way these coastlines align, as if they were meant to be together, is mesmerizing. It's easy to imagine this single, gigantic landmass stretching from one icy pole to the other, surrounded by a vast global ocean. But the most captivating thing about this story is that this was far from the first time our planet had assembled its continents into a single world. Pangea was just the latest act in a drama that has been repeating itself for billions of years. The reason the continents move at all is because the surface of our planet isn't a solid, immobile shell. It's alive and restless. Deep beneath the crust lies the mantle, a layer of molten rock that, on the scale of geologic time, flows like incredibly thick tar. Heat rising from the planet's interior creates gigantic, slow-moving convection currents. These currents cause the solid slabs of the crust to drift across the surface like vast ice flows in a choppy sea. This process, known as plate tectonics, continually reshapes the Earth. Oceans are born and disappear. Mountains rise to the heavens and are ground to dust. And continents travel thousands of kilometers over millions of years. It's an eternal, shifting puzzle, never fully solved and constantly reassembling itself. Pangea is so important to us because it's easiest to recreate in our imagination. The continents we live on today were once its constituent parts. The coastlines we see on maps were once land borders. There's something almost personal about it, like picking up the pieces of a broken plate and all the cracks line up perfectly. But travel further back in time, and these fragments don't just fit together differently, they begin to change shape. Coastlines erode, new landmasses rise from the ocean. Volcanic island arcs stitch continents together, while giant rifts tear them apart. The further we go into the past, the more difficult it is to recognize a familiar picture. It's like trying to reconstruct an old photo album where half the pages have been torn out, and the faces in the remaining pictures have changed beyond recognition with age. This is precisely the challenge geologists face when they attempt to peer beyond the era of Pangea. They have only fragments of ancient evidence, fragments of long-eroded mountain belts, tiny mineral grains that retain magnetic signatures indicating their ancient location. But when all these disparate clues are pieced together, they form a clear pattern. Earth has repeatedly gathered and scattered its continents, passing through great cycles, each lasting hundreds of millions of years. To understand this process, imagine a gigantic heartbeat of the planet. The heart contracts, drawing the continents together, and then expands, pushing them apart. The Earth's crust behaves much the same way. The continents drift apart, scattering across the planet, and then forces, operating within its depths, slowly but inexorably drive them back together, forming another supercontinent. Scientists call this process the supercontinent cycle. Pangea was only the most recent such compression. Before it, there were Rodinia, Nuna, Kenorland, and even more ancient and obscure continental embryos, such as Each such cycle dramatically altered the climate, sea levels, and life itself on Earth, leaving behind traces that we struggle to decipher today. But why do continents ever gather together? If tectonic plates move in different directions, shouldn't they simply drift chaotically, forever moving away from each other? The answer lies in the very geometry of our planet. The Earth's surface is a sphere. It's finite. When an ocean expands in one place, like the Atlantic for example, the oceanic crust elsewhere must compress and subduct beneath the continents. As a result, continents once separated by ocean inevitably collide on the opposite side of the planet, forming new colossal mountain ranges. Imagine the Himalayas, the result of India colliding with Asia. Now multiply this titanic force by the scale of the entire planet, and you have the recipe for the creation of a supercontinent. This has happened again and again, each time transforming the face of the Earth beyond recognition. When Rodinia formed around 1.1 billion years ago, almost all of the planet's landmass was merged into a single gigantic landmass. Its interior likely consisted of sun-baked, barren deserts, thousands of kilometers from the life-giving waters of the oceans. The planet's climate oscillated between severe extremes. Later, as Rodinia began to break apart, this massive land redistribution likely triggered one of the most severe ice ages in history, the Snowball Earth era, when ice may have covered the entire planet from the poles to the equator. Nuna, which existed about 1.6 billion years ago, is much less well known. Rocks from that era are extremely rare and heavily altered by pressure and heat. But the evidence we do have suggests that parts of modern North America, Scandinavia, Siberia, India, and Australia were once stitched together into a single slab. Its mountains have long since turned to dust, but ancient cratons, the stable cores of continents, still bear the scars of those titanic events. And Kenorland, which formed about 2.7 billion years ago, was one of the first true supercontinents. Imagine the modern continents, a gigantic mosaic assembled from pieces of frozen fire, held together by the scars of ancient mountain ranges. Every continent we live on today owes its birth to volcanic fury that raged millions of years ago. Without volcanoes, solid land as we know it simply would not exist. Our planet would be covered only by a thin basaltic crust of the ocean floor, which would be eternally absorbed by the depths of the hot mantle. But the Earth's fiery breath didn't just create land, it shaped life itself. This creative force had a dark side. Volcanoes were not only the architects, but also the executioners of the ancient world. Their eruptions were truly catastrophic. Gigantic clouds of ash could blot out the sun for decades, plunging entire oceans into darkness and destroying ecosystems. Toxic gases escaping from the Earth's depths poisoned the atmosphere, turning the air into a deadly cocktail. The greatest mass extinctions in the planet's history were often directly linked to such events, when, over thousands of years, volcanoes spewed so much carbon dioxide into the atmosphere that the climate changed beyond recognition. Perhaps the most terrifying example is the eruption of the Siberian traps approximately 252 million years ago, which coincided almost entirely with the Great Permian extinction. But even long before that, in the eras preceding the emergence of the supercontinent Pangea, similar fiery cataclysms had colossal consequences, completely clearing the stage for life and paving the way for new evolutionary experiments. Yet volcanoes didn't just kill. They also nurtured life. Imagine underwater hydrothermal vents, true oases created by volcanism. These black smokers may have been the cradle of the very first microbial communities on Earth, providing them not with sunlight but with pure chemical energy. Geysers, hot springs, newborn volcanic islands, and entire underwater mountain ranges all created unique, isolated worlds where life could not only survive but thrive, inventing ever-new metabolic pathways. Even in the harshest times, when the planet's atmosphere was hostile, these volcanic pockets served as a safe haven, a laboratory for evolutionary innovation. To transport oneself mentally to the world before Pangea is to see a planet completely dominated by the element of fire. Endless chains of smoking volcanic islands stretched along the coasts of ancient continents. Fiery fountains erupted regularly on the horizon, and gigantic cracks, future rift zones, spread in the very hearts of the supercontinents. Molten lava covered areas hundreds of thousands of square kilometers in size, and these solidified seas of fire later transformed into vast basalt plateaus. The sky overhead was often crimson with volcanic ash, and the acrid smell of sulfur wafted on the wind across the prehistoric oceans. It was a harsh, inhospitable world, yet incredibly fertile, constantly reshaping itself and preparing the stage for future eras. The gases emitted by volcanoes left their mark on history for millions of years. Carbon dioxide, CO2, acted like a giant blanket, warming the planet and periodically plunging it into extreme greenhouse periods. Sulfur dioxide, SO2, conversely, although it didn't linger in the atmosphere for long, could cause sharp and devastating cooling by reflecting sunlight back into space. These constant climate swings, hot and cold, created incredible evolutionary pressure. Ancient species had to adapt not only to changing landscapes, but also to a climate that could change dramatically in the blink of an eye due to yet another burst of volcanic activity. Ancient Earth left us its diaries, and scientists are now learning to read them. Thick layers of basalt in rocks are frozen evidence of colossal eruptions of the past. Microscopic zircon crystals are found in layers of volcanic ash, acting like perfect clocks, allowing us to date these events with incredible precision. And the chemical composition of marine sediments preserves information about isotopic anomalies that indicate sharp spikes in atmospheric CO2 caused by volcanic pulses. All this evidence fits together to form a coherent picture. Fire was an eternal and constant companion to the great dance of continents and the cycles of the assembly and disintegration of supercontinents. Volcanoes serve as a constant reminder that Earth is not a dead rock floating through space. Our planet is alive, and its life manifests itself in precisely this way. Incredible heat emanating from its very core causes the mantle to slowly churn, like soup in a giant cauldron, and this energy finds release in eruptions on the surface. Long before the advent of humans, long before the age of dinosaurs, and even long before the first animals developed skeletons, this inexorable process endlessly reshaped our world. And this restless, fiery breath of the planet has never stopped, and will not stop for billions of years, until its heart finally cools. If we had the opportunity to stand on the surface of Earth during the time of ancient supercontinents like Rodinia, Nuna, or Kenorland, the sight that would unfold before us would be truly stunning. Rivers of molten lava stretching from horizon to horizon, fountains of molten rock illuminating the inky night sky. Colossal volcanic mountains that would make modern-day Everest pale in comparison, spewing columns of ash into a strange, alien atmosphere. Yet, amidst all this chaos and destruction, quiet, creative processes were also underway. The new crust slowly cooled and hardened, giving birth to new minerals and raising fresh land masses from the sea depths. And just as volcanoes created continents, they also created oceans. Deep underwater, eruptions created mid-ocean ridges, where new crust was born from faults and streams of superheated, mineral-rich water erupted from the depths. These streams became veritable oases for primitive microbial life. Even in today's oceans, in complete darkness and under monstrous pressure, such communities thrive at hydrothermal vents, drawing energy not from the sun, but from the Earth's own chemistry. It's not hard to imagine that such ecosystems were common in the deep past, hundreds of millions of years before the first animals appeared. Volcanism was the very engine that sustained life on the planet. The great rhythm of fire and stone accompanied absolutely every stage of Earth's history. Each time supercontinents converged, fiery volcanic arcs grew along their edges, and each time they began to crack at the seams and disintegrate, streams of lava erupted from gaping fissures. Fire was both the beginning and the end of every great continental cycle. Continents burned, collapsed, reshaped, and reassembled, while the land beneath them continued its restless life. But volcanoes were only one manifestation of this internal planetary unrest. Earthquakes, or tremors, were also constant companions of continental drift. They shook ancient landscapes as the Earth's crust buckled, cracked, and unleashed pent-up fury. Today, when we hear the word earthquake, familiar names spring to mind: Japan, California, Turkey, Chile. These regions are constantly in the news because they lie on modern, active tectonic plate boundaries. Fault lines are visible to the naked eye, and seismic waves constantly remind us how fragile the ground beneath our feet truly is. But earthquakes have always occurred everywhere. Their geography is not limited to modern seismic zones. Billions of years ago, long before Pangea, Rodinia, or Nuna, tremors accompanied every plate movement, shaking a world we would not even recognize today. To understand this, it's enough to remember that an earthquake is simply the planet's way of releasing stress accumulated in the crust due to the movement of giant tectonic plates. These plates collide head-on, slide sideways against each other, or slowly move apart. The crust bends, stretches, and compresses like a spring until the stress reaches a critical point. Then a sudden break occurs, releasing enormous energy that spreads in all directions as seismic waves. The tremor itself may last only a few seconds, but its consequences, giant landslides, devastating tsunamis, and shifting river courses, changed the landscape forever. Plate tectonics has been active on our planet for billions of years, meaning earthquakes have been an integral part of Earth's history practically since its inception. In the pre-Pangean era, the contours of the continents were completely different, but the physical principles remained the same. When supercontinents like Rodinia formed, their margins became zones of incredibly intense seismic activity. At subduction zones, one plate crushed another, generating chains of earthquakes that stretched for thousands of kilometers. And when these supercontinents began to break apart, internal cracks tore them apart, and each stage of this great rift was accompanied by powerful tremors. There were simply no completely safe and stable places on the planet. The only difference was that the world map looked different, and the oceans had different names. The fault lines have since either shifted or become overgrown and disappeared. But the scars of those ancient earthquakes can still be seen in the geological record. Faults cut through ancient rock masses like knives, revealing places where the crust once split under unimaginable forces. Metamorphic rocks bear the imprint of monstrous pressures, imprinting moments of ancient seismic shocks in stone. Petrified underwater landslides serve as silent witnesses to catastrophes of the distant past. And while we will never be able to measure the precise magnitude of earthquakes that occurred hundreds of millions of years ago, these scars on the planet's surface tell us they were no weaker than modern ones, and sometimes perhaps even more powerful. Imagine standing on the shores of the ancient Iapetus Ocean just as it was beginning to form. The ground beneath your feet trembles. gaping cracks open in the crust and molten magma rises from the depths. Or imagine yourself transported to the very heart of the supercontinent Rodinia. Here, along future rift zones, deserts are forming, foreshadowing a great rift. The planet trembles unpredictably, the Earth cracks, and rivers suddenly change their courses. For primitive life, which then lived mostly in the seas, these events on land likely passed almost unnoticed. But the planet itself never knew a moment of peace. Its crust was never truly stable. Earthquakes were also inextricably linked to the birth of mountains. When continents collided, their edges were crushed into gigantic folds, and seismic waves constantly traveled along the growing mountain ranges. The formation of the Grenville mountain belt, associated with the assembly of Rodinia, must have been accompanied by countless earthquakes. Later, when these mountains were eroded away, ancient faults at their base remained and could be activated again and again. Even today, some earthquakes occur in seemingly stable central parts of continents. These are nothing more than echoes of ancient tectonic scars, fault lines that have never fully healed over hundreds of millions of years. But earthquakes didn't just destroy, they also created the environment. By fracturing rocks, they opened new pathways for groundwater circulation, facilitating the deposition of valuable minerals in veins. Many of the mineral deposits we exploit today owe their origins to these ancient processes. Earthquakes altered river courses, created new valleys and lake basins, thereby shaping future ecosystems. If you were an outside observer in that era, you wouldn't recognize the map of the Earth. The continents were completely different, coastlines curved in the most bizarre ways, and oceans stretched where land now stands. But the rumble of the shaking Earth and the trembling beneath your feet would be painfully familiar. It's one of the few constants in our planet's turbulent history. Scientists study ancient earthquakes not only through faults in solid rock, but also through so-called seismites. These are unique distortions in sedimentary rock layers left by powerful tremors. Imagine the soft, wet silt on the bottom of an ancient sea. When an earthquake occurs, this silt trembles and deforms. The sinkholes, folds, and cracks that formed at that moment froze forever as the sediment turned to stone. Some of these seismites are over 1 billion years old. This is direct, irrefutable evidence that earthquakes shook the seas long before the formation of Pangea. And this begs the question, were those ancient earthquakes more powerful than those we know today? Could ancient earthquakes have been more powerful than those we know today? In some cases, without a doubt. Imagine the scene. Gigantic supercontinents, the size of entire hemispheres, slowly but inexorably colliding with one another. The stress on the Earth's crust reached truly colossal proportions, and faults, like scars on the planet's body, could stretch for thousands of kilometers. A single such mega-earthquake was capable of releasing energy that dwarfs anything humanity had observed in the past few centuries. Events measuring 9.0 magnitude or higher were likely not all that uncommon in that ancient world. Of course, the living creatures of that era had no concept of seismology. Trilobites crawled on the floors of primeval oceans, armored fish swam in murky Devonian rivers, and primitive microbial mats clung to life along rocky shores. But they all experienced the full impact of these cataclysms. Coral reefs collapsed into the abyss. Tons of sediment rose from the seabed, turbiding the water, and coastlines could be transformed beyond recognition in an instant. For them, the tremors of the Earth were as much a part of their environment as ocean storms or daily tides. Reflecting on the earthquakes of the pre-Pangean era serves as a powerful reminder that our planet was never static. We sometimes tend to imagine the early Earth as a calm, motionless globe that only became interesting with the emergence of life or shifting continents. But the truth is, the Earth's crust has always been in constant motion. It constantly accumulated and released colossal stress through these sudden, violent surges of energy. Only the map on which this geological drama unfolded changed. Today, we painstakingly map fault lines, measure every tremor, and build structures to withstand the elements. In that distant past, there was no preparation, no foresight, only the raw primordial interaction between rock and monstrous pressure. And yet, it was those ancient earthquakes that shaped the world we inherited. They carved deep troughs that would later become oceans, uplifted mountain ranges, and even influenced the location of rich mineral deposits. And just as earthquakes were the constant companions of the early continents, another, no less profound transformation was brewing on the planet, one associated with the emergence of forests. This change was as fundamental as any seismic shift. Long before Pangea, before the age of dinosaurs, and even before the first reptiles crawled onto land, something invisible to the eye began to change the face of the world. And this revolution took place on land. Plants that once clung timidly to the edges of lakes and shorelines, resembling tiny patches of moss, began their great journey. They grew taller, their structure became more complex, and their stems grew stronger. Millions of years passed, and they transformed into dense, endless green forests that stretched across continents, sheltering valleys, climbing hillsides, and casting deep shadows where for billions of years only bare rock had reigned. For us modern humans, forests are something taken for granted, almost eternal. But on the scale of Earth's history, they were a truly radical invention. The first forests didn't just change the landscape, they reshaped the composition of the atmosphere, altered the chemistry of the oceans, influenced the global climate, and set the stage for the emergence of entirely new, astonishing life forms. The earliest land explorers, as we've already seen, were small and primitive. They had no true roots, leaves, or wood. These fragile pioneers crouched low to the ground, surviving only in the wettest places, where they could absorb water with their entire surface. But evolution never stands still. By the Silurian period, around 430 million years ago, some plants had undergone a crucial improvement: the development of vascular systems. This complex network of internal tubes allowed them to transport water and nutrients throughout their bodies. This innovation became their ticket to freedom. It freed plants from the need to constantly be submerged in water. Now they could grow upward toward the sun, survive in drier soil, and boldly move into the interior of continents. The first vascular plants were still dwarfs by our standards, ranging from a few centimeters to a meter in height. A classic example is Cooksonia, a simple branched plant with a sporangia at the tips of its shoots. But even these humble ancestors gave rise to incredible diversity. As early as the Devonian period, approximately 390 million years ago, true trees appeared on the planet. Archaeopteris is often considered the first of them. This giant had powerful tree trunks, spreading branches, and true leaves, and could reach 30 meters in height, the equivalent of a modern 10-story building. Imagine this scene: walking through a landscape that for billions of years had known only bare rock and moss, and suddenly finding yourself in the shadow of towering tree trunks. It was a stunning, incomparable transformation. Once established, forests began to spread at an incredible rate. Club mosses, ferns, horsetails, and early seed plants formed dense, impenetrable thickets. Their powerful roots, like steel reinforcement, held the soil together, preventing erosion. Their foliage retained rainwater, slowing its runoff, and their trunks and branches created countless new homes for insects and other tiny organisms. Through photosynthesis, these green giants greedily absorbed carbon dioxide from the atmosphere and exhaled oxygen in return. This had a colossal, fateful impact on Earth's climate. During the Devonian and Carboniferous periods, forests sucked such enormous amounts of carbon dioxide from the air that global temperatures plummeted. Massive ice sheets began to form in the southern hemisphere, and atmospheric oxygen levels soared to levels unseen in almost the entire history of the planet. By some estimates, the oxygen content could have exceeded 30%, compared to just 21% today. This enriched air allowed for the existence of true giants of the arthropod world. Imagine millipedes the size of cars, dragonflies with wingspans of almost a meter, and scorpions significantly larger than their modern relatives. They thrived in this atmosphere because the high oxygen content allowed their relatively inefficient respiratory systems to support their enormous bodies. Forests also changed the soil itself. Before the advent of rooted plants, the soil layer was thin and consisted primarily of weathered rock with minimal organic matter. The spread of forests led to the formation of thick, fertile soils filled with decaying leaves, roots, and wood. These new soils retained moisture and nutrients, dramatically altering the hydrology of the land. Rivers became calmer, their channels meandering, forming complex networks that simply didn't exist before. Marshes and wetlands expanded, creating entirely new ecosystems. The land became more dynamic, diverse, and teeming with life. This impact also reached the oceans. Nutrients leached from forest soils into rivers and then into the seas, triggering a thriving marine life. And the entombment of vast amounts of organic carbon in forest soils and wetlands led to a further decline in atmospheric carbon dioxide concentrations, triggering global cooling. The interaction between forests, the atmosphere, and the oceans became one of the most significant ecological shifts in Earth's history. The Carboniferous period, which lasted from approximately 359 to 299 million years ago, was named for the gigantic coal deposits that formed during this period. This is a direct legacy of those very first forests. Vast swampy jungles dominated by tree-like club mosses such as Lepidodendron and Sigillaria stretched across the planet's equatorial regions. Their scale-like trunks, covered in patterns, soared up to 30 meters into the sky. When these giant trees died, their remains fell into the swampy soil, where decomposition proceeded very slowly due to a lack of oxygen. Over millions of years, heat and pressure transformed these buried forests into coal. Essentially, the energy we still burn in our furnaces is sunlight stored by the first forests hundreds of millions of years ago. A walk through such an ancient forest would have felt like a journey to another planet. The trees here were completely unlike the oaks and pines we are accustomed to. Many had strange, thorny trunks, crowns of gigantic leaves, or enormous spores instead of seeds. The damp, marshy soil squished underfoot, and the air was filled with the buzz of insects far larger than we can imagine. Amphibians lurked in the swamps, some reaching the size of crocodiles. It was a world halfway between the ancient seas that once dominated the planet and the terrestrial ecosystems we know today. Forests changed not only the biology, but also the geology of the planet. By sequestering enormous volumes of carbon in the form of coal and organic deposits, they altered the gas balance in the atmosphere. This cooling effect may have contributed to the onset of ice ages in the late Carboniferous and early Permian. The cycle of forest expansion, carbon sequestration, and climate change became one of the most important feedback systems in the ancient world. The growth of forests also spurred new evolutionary breakthroughs. Insects rapidly diversified to exploit new food sources. Some learned to fly, flitting between giant plants and feeding on their spores or sap. Amphibians found refuge in countless forest pools, and early reptiles took a decisive step toward completely conquering land. They began laying eggs with hard, protective shells, forever freeing them from the need to return to water to reproduce. Forests created new ecological niches, and life filled them with astonishing speed. In many ways, the first forests were Earth's greatest experiment in creating complex ecosystems on land. They built these systems themselves, creating forest layers, the high canopy, the understory, and the forest floor. Their emergence forever altered the water and nutrient cycles and gave rise to new, complex interactions between the atmosphere, lithosphere, and biosphere. Once they emerged, there was no turning back. Forests became an integral part of the planet, constantly evolving, but never completely disappearing. Scientists have been able to trace this monumental history through wood fossils, leaf imprints, and spores, as well as coal seams and the isotopic composition of ancient rocks. This evidence suggests that the transition was gradual, but its consequences were revolutionary. In just a few tens of millions of years, the continents of our planet transformed from barren deserts into lush, green oases, from silent spaces into worlds filled with the buzz of insects and the croaking of amphibians. It's hard to overstate how profoundly forests have impacted our planet. They didn't just add greenery to the Earth, they redefined the very relationship between land, air, and life. In many ways, forests made our modern world possible. The oxygen we breathe, the soils we grow, and the climate systems on which our existence depends all have their origins in those ancient primeval forests. And as they spread across the planet, they became home to creatures that grew larger, more complex, and more powerful. Fast forward to an era when the world became a realm of giants, wondrous and bizarre creatures, the likes of which the planet had never seen. Imagine a world where the air was so rich in oxygen that it allowed life to take on truly colossal forms. In this world, giant arthropods thrived, crawling, running, and flying in the shade of colossal prehistoric trees. At that time, long before the great continent of Pangea took its final shape, vast forests sprawled across the planet. They not only painted the landscapes green, but also created entirely new arenas for evolution. The atmosphere was supersaturated with oxygen, its concentration higher than at any time in Earth's history. The ground beneath was soft and moist, swamps stretched everywhere, and the dense crowns of giant ferns and horsetails provided reliable shelter. It was into this world that the first creatures to conquer land stepped. Some of them crawled straight from the ocean depths, others only timidly took their first steps along the water's edge, but there were also those who completely severed their connection to the watery element and adapted to life among roots and fallen leaves. And the results of this great exodus were truly astonishing. Giant arthropods reigned supreme on land, dwarfing their modern descendants. Enormous amphibians explored the marshy outskirts of forests, and the first reptiles, learning to lay eggs directly on land, were forever freed from the shackles of the aquatic world. Arthropods were among the earliest and most successful conquerors of land. By then, they had already thrived in the oceans for hundreds of millions of years, and their durable exoskeletons, like knight's armor, provided both protection and support when they ventured out of the water. The pioneers were centipede-like creatures that slowly moved across the moist soil, feeding on rotting plant remains. Others soon followed: scorpions, true centipedes, and primitive insects. However, it was during the Carboniferous period, approximately 300 million years ago, that these creatures reached truly monstrous sizes. Just imagine a centipede over 2 meters long and as wide as a small dog. It was one of the largest invertebrates to ever crawl on our planet. This monster's name was Arthropods. This giant inhabited swamp forests, feeding on decaying vegetation, and likely had few enemies capable of challenging its size. Such incredible dimensions were possible only because of one thing: the extremely high oxygen content in the atmosphere. Modern estimates place the level at over 30%, while today we breathe air containing only 21% oxygen. Arthropods breathe through a complex network of tubes called tracheae, which deliver oxygen directly to their tissues through a simple process of diffusion. The higher the oxygen concentration in the air, the larger the body size this respiratory system can support without suffocating. Flying insects also seized their opportunity in this oxygen-rich world. Imagine a dragonfly with a wingspan reaching almost a meter. These creatures soared above prehistoric forests and swamps like miniature airplanes. Such enormous sizes are impossible for them in our modern world, but in the skies of the Carboniferous period, they were unrivaled masters of flight and among the top aerial predators. Their enormous compound eyes, already sophisticated, gave them a huge advantage in finding prey, and their powerful wings allowed them to patrol vast territories. Scorpions and spiders were also significantly larger than their modern relatives and hid in the dark, damp forest undergrowth. Imagine wandering through this primeval forest ankle-deep in ferns and suddenly spotting a scorpion as long as your forearm crawling along the ground. The abundant oxygen and inexhaustible food supply provided by the lush vegetation allowed arthropods to thrive in ways that now seem pure fantasy to us. But they weren't the only ones to take advantage of the new environment. Amphibians also emerged from the water onto land, ready to master this new habitat. Their ancestors were lobe-finned fishes, creatures that developed strong, fleshy fins and primitive lungs. Tiktaalik, a famous fossil that lived around 375 million years ago, perfectly exemplifies this transition. It combines features of both fish and amphibians. It has fins with wrist-like bones, but also lungs and gills. Its flat head was ideal for emerging from the water and surveying its surroundings. It was from such transitional forms that the first true amphibians evolved. During the Carboniferous period, amphibians were incredibly diverse and often reached enormous sizes. Some resembled giant salamanders, while others resembled ferocious, crocodile-like predators that lurked in the swamps awaiting prey. They were still tied to water, as that's where they laid their eggs, but even in these swampy lands, they were at the top of the food chain. Their diet included fish, giant insects, and smaller amphibians. Their success was inextricably linked to the forests and swamps that covered the continents, providing them with both shelter and food. However, amphibians had serious limitations. They relied entirely on water for reproduction, and their skin constantly required moisture. Overcoming these barriers and truly conquering land required a new evolutionary breakthrough. And it arrived with reptiles. Around 310 million years ago, some animals still resembling amphibians began laying eggs with a tough protective shell. These so-called amniotic eggs could survive on land, reliably protecting the embryo from desiccation. This was a true breakthrough, completely freeing vertebrates from their dependence on water bodies. Reptiles could now lay eggs deep in forests and at elevated sites, colonizing territories completely inaccessible to amphibians. The very first reptiles were small and resembled modern lizards, but their innovation led to colossal changes in the animal kingdom. Over time, reptiles gave rise to an incredible diversity of forms, from predators with enormous sails on their backs, such as Dimetrodon, to the distant ancestors of dinosaurs, birds, and even mammals. But here, in the Carboniferous and Permian periods, they were just beginning their great journey, competing with giant amphibians for dominance in the forests and swamps. The interactions between these groups created the unique ecosystems of the time. Giant arthropods, feeding on decaying plants, played a key role in nutrient cycling. Insects and smaller arthropods, in turn, became prey for amphibians and reptiles. Amphibians reigned in wetlands, while reptiles began to explore drier areas. It was a complex, intertwined system where life explored every conceivable route. Let's imagine walking through one of these forests. The ground beneath our feet would be damp and springy, and the air would be filled with the dense buzz of insects, much larger than those we're accustomed to today. The air itself would feel heavy, dense, and saturated with oxygen, perhaps even too invigorating for our lungs. Giant dragonflies would flit overhead, their wings reflecting the dim light. Somewhere in the dim undergrowth, the rustle of a giant centipede would be heard. Amphibians would splash in puddles, watching our every movement with their enormous, unblinking eyes. Nimble reptiles would scurry between the tree roots everywhere. This world would seem simultaneously alien and achingly familiar, like a first rough draft of the ecosystems we see on Earth today. But the era of these giants couldn't last forever. Toward the end of the Carboniferous period, atmospheric oxygen levels began to decline, and all the advantages it had provided disappeared. Arthropods began to rapidly shrink until they reached the sizes we see today. Amphibians also became smaller, ceding ever-new ecological niches to more adaptable reptiles. The Carboniferous giants were the product of a unique environment that allowed life to expand its boundaries. However, their legacy proved immortal. Early evolutionary experiments with arthropods, amphibians, and reptiles laid the foundation for all future ecosystems. Insects became the most diverse group of animals on the planet. Amphibians, though reduced in size, still exist alongside us as frogs and salamanders. And reptiles became the ancestors of the great dinosaurs, birds, and all mammals, including us. And although the giants of the Carboniferous period are long gone, the evolutionary path they blazed continues to this day. In many ways, this was the birth of a new era. At this moment, the Earth truly came alive in all its dimensions. Plants had already transformed the atmosphere and soil, but it was with the emergence of animals who mastered the forests, swamps, and skies that the planet became truly dynamic, noisy, and complex. New relationships between predators and prey developed, food chains expanded, and ecosystems became increasingly resilient. The conquest of land by these ancient giants was not just another stage, but the true beginning of modern terrestrial life. While these complex ecosystems evolved, the continents themselves continued their slow, inexorable drift, approaching the moment when they would coalesce into a single supercontinent, Pangea. The stage was set for a new world, where life on land would collide on a scale never before seen. To understand what a collision of continents means, it's enough to look at the modern world. We see India smashing into Asia, lifting the Himalayas skyward. Earth's history has seen many such cataclysms. The formation of the supercontinent Pangea was one of them, but even this monumental event is only a small part of what was happening to our planet. More ancient land unions were not simply local processes, but global catastrophes that stitched entire continents together. And each time this happened, not only the face of the Earth, but the entire world of living things changed. It all began with a titanic, unimaginably slow dance. Imagine the ancient rocky hearts of the continents, blocks known as cratons, billions of years old. They glided slowly across the planet's molten mantle, driven by the inexorable force of tectonic plates. The oceans that separated them slowly disappeared, consumed by fiery fissures in the crust, subduction zones. And now, after an eternity, they met. The moment of impact was apocalyptic. The Earth's crust, unable to withstand such colossal pressure, crumpled like paper, rising to the heavens in monstrous mountain ranges. Waves of earthquakes swept across the planet, shaking its very core, and along the seams where the continents met, volcanoes erupted in fiery chains, spewing ash and lava. These global cataclysms weren't simply destruction. They were acts of creation, writing a new chapter in Earth's history, forever changing its appearance, and with it, the fate of all life. It's important to understand, these collisions weren't instantaneous events. They stretched out over tens of millions of years. For humans, such a span of time is an eternity. But on a geological scale, these were sudden, decisive moments that determined the planet's future. Let's travel back in time to witness one of the first such events. Around 1.8 billion years ago, small, disparate landmasses began to converge. This monumental process led to the birth of one of the first supercontinents, which scientists named Nuna. It was a gigantic landmass that occupied a vast portion of the young planet's surface. The scars of that titanic battle are still visible in the oldest rocks hidden deep within Canada, Greenland, and Siberia. And then, about 1.1 billion years ago, history repeated itself, but on an even grander scale. The era of Rodinia had arrived. Continental blocks once again came together in a deadly embrace, sparking colossal orogenic processes, the scientific term for mountain building. As a result, mountain ranges rose across the planet, their peaks towering higher than Everest, higher than anything we can see today. Time and erosion have long since erased these giants from the face of the Earth, but their deep granite roots remain within the crust. By studying them, we, like detectives, reconstruct the picture of those ancient geological dramas. Where worlds once collided, it wasn't just the terrain that changed. The consequences were global. New mountain ranges became impenetrable barriers to the winds, completely reshaping the planet's climate map and altering precipitation patterns. This collision also altered the planet's bloodstream, the circulation of the world's oceans. The seas that separated continents disappeared, and ocean currents rushed along entirely new routes. Of course, these events also affected life itself. Shallow seas teeming with primitive organisms disappeared, but in their place, new landscapes, new opportunities, new ecological niches arose. In those distant times, when the land was still a lifeless desert, the oceans bore the brunt of these collisions. New growing mountains washed tons of nutrients into the water, triggering a thriving ecosystem of microscopic life and altering the chemical composition of the seas. But millions of years passed, and life emerged onto land. When forests covered the continents and the first animals roamed them, plate collisions began to reshape entire ecosystems on land. One of the most monumental events of this kind unfolded in the late Paleozoic. The colossal continent of Gondwana was advancing from the south. Laurasia and Laurussia were already drifting toward it. For millions of years, they inexorably drew closer, and then, approximately 335 million years ago, they collided. Thus was born Pangea, the supercontinent almost everyone has heard of. This colossal collision led to the closure of the ancient Racum Ocean. In the place of its destruction, mountain ranges arose, the remains of which we know today as the Appalachian Mountains. The planet's climate changed beyond recognition. Lifeless deserts spread across the heart of the gigantic continent, while along the equator, marshy, swampy forests flourished, providing a home for giant insects and the first amphibians. The birth of Pangea was one of the greatest geological events in history, but only the latest in a long series of such dramas that spanned billions of years. If we could find ourselves at the epicenter of such a collision, the sight would be forever etched in our memories. Imagine the coastline of another world slowly appearing on the horizon, where there had always been only ocean. Day by day, it grows closer. The sky darkens with the ash of countless volcanoes, and the ground beneath your feet constantly trembles, as directly beneath you, the oceanic crust thunders into the fiery bowels of the planet. Rivers, flowing along the same channel for centuries, suddenly encounter a growing mountain and are forced to find a new path. These changes didn't happen overnight, but their effects, cumulative over generations, were obvious. Where waves once lapped, impenetrable cliffs now towered. Calling these events a catastrophe from the perspective of life wouldn't be entirely accurate. They were simply new rules of the game to which life had to adapt. Trilobites, brachiopods, and corals evolved alongside their seas. Amphibians and the first reptiles colonized the new forests and plains that emerged where continents collided. Life, as always, found a way to survive and adapt. Each such collision was a global restructuring. The world map was redrawn, and the laws of climate and habitat were rewritten from scratch. The very idea of supercontinents, born in the fires of collisions, implies that they are not eternal. Just as continents converged, closing off oceans, so millions of years later, the process of rifting, breaking apart, torn them apart, opening up new seas. Mountains that once supported the heavens were eroded by wind and water, and their remains, in the form of sand and silt, were carried into new oceans. It is a great and endless cycle, and collisions are only one part of it. But it is they that leave the deepest scars on the planet. The granite roots of ancient mountains, the folded belts of rock. All these are clues pointing to places where ancient worlds once converged. Geologists can trace these ancient seams by finding similar rock types on continents that are now separated by thousands of kilometers of ocean. For example, the Appalachian Mountains in North America are geological twins of mountains in Scotland and Norway, providing direct evidence that Europe and the Americas were once a single entity. Similarly, the geology of West Africa perfectly matches the structure of the east coast of South America, a reminder of their shared past as part of Gondwana. These threads, stretched across time, allow us to reconstruct the lost geography of ancient worlds and understand the scale of the cataclysms that shook our planet. Their meeting was like a firestorm. Subduction zones, where one tectonic plate subducts beneath another, gave birth to entire archipelagos of volcanoes. As the continents collided, magma from the Earth's interior surged upward, forming gigantic underground reservoirs that, as they cooled, became new granite rocks. The planet's atmosphere changed, saturated with gases from thousands of eruptions. These events were not quiet. They were fiery, thunderous, changing the very face of the world. The birth of a supercontinent is not simply the slow compression of two landmasses. It is a complex process involving mantle convection, plate movement, erosion, and volcanism, working in a single furious tandem. And each time a new world was born, it was unlike the last. Reflecting on these titanic collisions, we understand how dynamic and vibrant our planet has always been. The continents that seem to us symbols of immutability are, in fact, eternal wanderers. They have been torn apart and reconstituted countless times. Each collision was both an end and a beginning, the end of one ocean and the birth of a new land. But these cataclysms, paradoxically, also created stability. The thickened continental crust arising at the collision sites formed those very durable cores, cratons, that can survive billions of years. The very land on which we stand owes its strength to these ancient alliances. As we explore this history, we inevitably come to the most famous of them, the final act that led to the formation of Pangea. But first, it's worth looking at Gondwana, the southern giant that played a key role in this drama. Throughout Earth's history, the most significant changes have come from within: continental drift, volcanic eruptions, mountain growth. But from time to time, forces from without, from the cold silence of space, have intervened. Asteroids and comets, these icy and rocky wanderers ploughing the vastness of the solar system, have repeatedly struck our planet. Sometimes their impacts went almost unnoticed, but at other times the impact was so monstrous that it led to the destruction of entire ecosystems. Long before the age of dinosaurs, even before Pangea had even split apart, collisions occurred that could alter the orbits of planets and perhaps even influence the very origin of life. They serve as a dire reminder. Earth is not an isolated oasis, but part of a much larger and more violent universe. When we look at the night sky, we see the scars of these cosmic encounters on the moon's face, craters forever etched on its surface. Our planet has endured just as many, and likely many more, such impacts. But plate tectonics, wind and water, the great healers, have erased most of these wounds. And yet, some ancient impact structures remain, and they can tell us their stories. Stories of how, long before forests, dinosaurs and mammals arose, the fate of our planet was decided by impacts from space. One of the oldest known scars is the Vredefort crater. Let's travel back 2 billion years to what is now South Africa. On that day, a giant asteroid fell from the sky. The shockwave from the impact was so powerful that it can be compared to the simultaneous detonation of billions of atomic bombs. A wound over 300 kilometers in diameter was left on the planet's surface. Any modern metropolis would seem like a tiny speck at the bottom of this gigantic crater. Of course, life on Earth at that time existed only in the form of microbes, but the consequences of this impact would have been colossal for the entire planet. Shock waves circled the globe many times over. Molten rock rained down from the skies, and the global climate was dramatically altered by trillions of tons of dust and gases ejected into the atmosphere, blocking the sun for many years. Another monumental collision occurred approximately 585 million years ago in the area that is now. Let's go back in time to a place that billions of years later would become known as the Canadian city of Sudbury. Here, in time immemorial, a colossal object fell from the sky. The impact created a gigantic scar on the planet's surface, the Sudbury River Basin stretching a full 200 kilometers across. To date, it is one of the largest and most proven asteroid impact sites on our planet. The impact's energy was so great that the Earth's crust literally boiled, turning into lakes of molten magma. Cooling over centuries, this molten rock formed incredibly rich deposits of nickel and copper. The space traveler didn't simply change the landscape, it unknowingly left behind countless treasures for future civilizations, treasures that humans would only begin to mine eons later. By the time the first multicellular life emerged and began its triumphant march in the primordial oceans, our planet remained a defenseless target for such cosmic attacks. Imagine the world approximately 600 million years ago, during an era paleontologists call the Ediacaran period. It was then that another asteroid struck what is now Australia, an impact that likely caused severe damage to fragile, nascent ecosystems. Unfortunately, evidence of that catastrophe survives only in fragments. During subsequent geological eras, the Cambrian and Ordovician, Earth continued to be bombarded incessantly from space. The scars of those impacts, ancient craters, can still be found in Sweden, Canada, and the United States. These were mostly localized events, capable of wiping out entire regions, but did not threaten life on the planet as a whole. However, they served as a grim and constant reminder that life evolved in a hostile environment, where destruction could strike from the skies at any moment. But some impacts were far more devastating than mere regional cataclysms. Around 465 million years ago, during the Ordovician period, the planet found itself caught in a crossfire. Two giant celestial bodies collided in the asteroid belt, creating a devastating cloud of debris. For millions of years, this deadly swarm rained down on Earth, leaving dozens of new craters on its surface across the globe. Some scientists theorize that it was this relentless bombardment that triggered global climate change, which in turn triggered the Ordovician mass extinction, one of the first and most devastating catastrophes in the history of life. This extinction, which occurred approximately 444 million years ago, was a death sentence for 85% of all marine species. It is traditionally attributed to a sharp global cooling and a drop in sea levels, likely caused by the growth of ice caps on the supercontinent Gondwana. However, cosmic impacts may have played a fatal role in this tragedy, proving the final straw for ecosystems already desperately struggling to survive in changing conditions. Among the victims were countless trilobites, brachiopods, and ancient organisms that built the first reefs. It took millions of years for marine communities to recover from this blow and begin a new round of evolution. Later, in the Devonian period, history repeated itself. A cosmic impact once again coincided with an era of global crisis. The Devonian was a time of tremendous evolutionary breakthroughs. The oceans teemed with diverse fish, plants were actively conquering land, and the first amphibians timidly emerged from the water, taking their first steps on land. But this prosperity was destined to be cut short. Between 375 and 360 million years ago, the planet was engulfed in a long and painful series of extinctions. Scientists still fiercely debate the causes of this catastrophe. Among the main suspects are abrupt climate change, oxygen depletion in ocean waters, and powerful volcanic eruptions. But even here, cosmic intervention was likely involved. Craters dating from this time have been discovered in North America and other parts of the world. This is direct evidence that the Earth is once again under attack at the most vulnerable moment for its ecosystems. The end Devonian extinction dealt a devastating blow to marine life. Majestic reef systems collapsed, requiring tens of millions of years to even partially restore their former glory. Placoderm fishes, encased in bony armor and once the undisputed masters of the deep, declined and soon disappeared completely. But among the survivors were early sharks, bony fish, and the ancestors of tetrapods, the very creatures that would eventually give rise to amphibians, reptiles, and mammals. As with other great extinctions, the demise of some cleared the way for the evolutionary triumph of others. However, not every visitor from space brought total destruction. Smaller impacts were an integral part of Earth's ancient environment, a kind of background noise, random jolts that could cause trouble but did not lead to global catastrophe. Moreover, some scientists believe that at the dawn of life's history, these impacts may have played a constructive role. One theory is that asteroids and comets delivered water and complex organic molecules to the young Earth, essentially seeding it with the key ingredients of life. Others suggest that the colossal energy of the impacts created unique conditions in which complex chemical reactions could occur, kickstarting biological processes. From this perspective, space travelers were simultaneously ruthless destroyers and potential creators of life. Mass extinctions were rarely the work of a single culprit. More often, they resulted from a complex array of destructive factors that simultaneously impacted the biosphere. Volcanic eruptions, climate change, and sea level fluctuations, all of these individually created stress, but acting together, they pushed ecosystems beyond the brink of survival. And while aliens from outer space weren't permanent killers of life, their appearance at the wrong moment could be that fatal blow that upset the fragile balance and set off a chain reaction of destruction. Imagine this day, a day like no other. A blinding flash in the sky, rapidly expanding, transforming into a new, scorching sun. And then a shockwave, splitting the very air, hotter and more deafening than anyone could imagine. Forests ignite like matchsticks, oceans rise in monstrous tsunamis, and millions of tons of dust and ash rise into the atmosphere, blocking the planet from sunlight for years. The impact itself lasts only a few moments, but its effects will be felt for thousands, perhaps millions of years. Long before the age of dinosaurs, these cosmic events actively shaped the history of our planet. They were a catalyst for evolution, forcing life to adapt, change, and seek new paths. They destroyed some, but in doing so, they gave others a chance. Without these uninvited guests from space, the history of life might have been much slower and more predictable, with far fewer dramatic twists. And while the Earth shook from external impacts, its own internal forces never ceased their work. The continents continued their slow, inexorable drift. Oceans were born and died, and volcanoes erupted with lava. Over hundreds of millions of years, the long journey toward unification into a single supercontinent, Pangea, took place. Vast landmasses slowly converged, drawn by the powerful tectonic forces that have always governed this great cycle. The history of Pangea is often portrayed as appearing out of nowhere, like a single monolith suddenly rising from the ocean, but the reality was far more complex and dramatic. The path to Pangea was a long journey, spanning hundreds of millions of years, a journey filled with violent collisions, breakups, the birth and death of entire oceans, and the construction of gigantic mountain ranges. The continents destined to become one were once scattered across the planet, each navigating its own path, pushed by deep currents in the Earth's mantle. Their convergence was not predetermined by some higher will, but was the inevitable result of the fundamental processes that govern life on our planet. To understand the origins of this great journey, we need to return to the era following the breakup of the previous supercontinent, Rodinia, which began to fragment around 750 million years ago. This breakup created new oceans, such as the Iapetus Ocean, which divided the territories that would later become North America, Europe, and parts of South America. The fragments of Rodinia drifted apart, and for tens of millions of years, the world became a patchwork of small continents. But it was precisely this split that created the conditions for a new, even greater unification. Over time, the individual fragments began to converge. Laurentia, the ancient core of North America, drifted toward the equator. Baltica, the prototype of northern Europe, slowly moved in the same direction, followed by Avalonia, a smaller fragment of the future Europe. Far to the south lay Gondwana, a colossal landmass encompassing modern-day South America, Africa, Antarctica, Australia, and India. Gondwana was already a giant then, and would eventually become the foundation around which all the other pieces of the puzzle would assemble. One of the key moments along this path was the closure of the Iapetus Ocean. As Laurentia, Baltica, and Avalonia converged, the ocean between them grew ever narrower. Subduction zones like giant conveyor belts pulled its floor into the planet's interior, inexorably drawing the continents closer together. Their collision, which occurred approximately 400 million years ago, was an event of titanic proportions. It led to the formation of the mighty mountain ranges that stretch across modern-day North America and Europe. The Caledonian Mountains in Scandinavia and the northern Appalachians in the eastern United States are the scars left by that great era. Meanwhile, the giant Gondwana continent moved north. Its collision with the newly formed continent of Euramerica took tens of millions of years. During this period, ancient oceans disappeared one after another. Volcanic arcs erupted, earthquakes shook the crust, and coastal shelves crumpled under the onslaught of advancing land. Approximately 335 million years ago, Gondwana and Euramerica finally collided, forming the core of the future Pangea. The Appalachian Mountains in North America, the Variscan Belt in Europe, and the Mauritanian Belt in Africa are all monuments to this grand union. But even this wasn't the end of the supercontinent's formation. Siberia, another large landmass, was also drawn into this planetary process. This craton, located to the northeast, was separated from the rest of the world by the Paleo-Ural Ocean. For millions of years, it slowly advanced, and around 300 million years ago, it slammed into the eastern edge of the supercontinent. This final great collision gave rise to the Ural Mountains, which to this day serve as a reminder of the final act in the drama of Pangea's birth. Imagine the end of a monumental geological process that lasted hundreds of millions of years. The final piece of a gigantic mosaic falls into place. Ancient Siberia, completing its long drift, collides with the other continents, and at that moment, Pangea is born. Now, it is not just a collection of landmasses, but a full-fledged supercontinent, a colossal landmass stretching from the ice cap of one pole to the other. On one side, it was washed by the boundless waters of the Panthalassa Ocean, while on the other, the more modest Tethys Sea jutted into the land. But this slow, titanic process of plate fusion didn't simply reshape the world map. It set off a chain reaction that forever altered the planet's climate, reshaped ecosystems, and sent evolution itself on an entirely new path. When the continents merged, vast inland territories were formed, untouched by the ocean's life-giving breath. As a result, gigantic deserts, comparable in area to modern continents, spread across what are now North America, North Africa, and Asia. At the same time, fierce monsoons raged along the coasts, bringing torrential rains. New mountain ranges, growing on the scars of collisions, redirected air currents and altered the usual precipitation patterns. All these global changes became a powerful driver of evolution. For plants and animals, the unification of lands and the conquest of new territories meant not just new horizons, but also deadly challenges. Species that had evolved in isolation on their continents for millions of years suddenly found themselves neighbors. The world became a gigantic arena where they were forced to compete for resources, desperately adapt to new conditions, or simply disappear from the face of the earth. Along the equator, in a hot and humid climate, lush swamp forests flourished, the remains of which, millions of years later, would become vast deposits of Carboniferous coal. Ancient amphibians and the first reptiles began their triumphant march through these forests and deserts, giving rise to ever new forms destined to rule the world in the following Permian era. But the unification of the continents brought not only life but also death. The merging of lands led to the disappearance of entire seas. Countless shallow coastal zones, the cradles of marine life, simply ceased to exist. Many marine species found themselves on the brink of extinction. The majestic coral reefs that flourished during the Devonian period could not withstand the dramatic changes in ocean chemistry and climate and began to collapse. The great extinctions that shook the planet at the end of the Devonian and Permian periods were directly linked to these tectonic cataclysms. If we could spin a time machine and compress millions of years into a few minutes, we would witness a truly mesmerizing spectacle. Before our eyes, the continents, like giant rafts in a boundless ocean of magma, slowly but inexorably converged. The oceans between them compressed and disappeared, and at the points of collision, like wrinkles on the face of an ancient god, new mountain ranges rose to the sky. Vast deserts spread across the interior of the newborn supercontinent. This movement was not linear. It resembled a complex, majestic dance. The continents sometimes drew closer, sometimes retreated slightly, but always obeyed the colossal forces hidden deep within the planet's bowels. Geologists today, like detectives, are reconstructing this great convergence from the clues left behind. Paleomagnetic data, frozen in ancient rocks, tell us where each continent was located at a given era. Fossils of the same species found on different continents provide irrefutable evidence that these lands were once a single entity. And mountain ranges and so-called suture zones are the scars left on the planet by these titanic collisions. When all these pieces of the puzzle fit together, a stunning picture emerges. Gradually, step by step, we see how the birth of Pangea was predetermined by the very logic of tectonic plate movement. But even what seems inevitable is never eternal. Like other supercontinents that existed before it and long ago disintegrated, Pangea was also doomed. Approximately 250 million years ago, at the moment of its greatest glory, the giant continent began to crack at the seams. Rifts appeared in its body, which over time turned into new oceans. The enormous landmass once again broke apart, eventually forming the continents we see on the map today. The journey to Pangea was incredibly long, but it was only one act in the endless play of our planet's tectonic life. Reflecting on this, we begin to understand. The Earth is not a frozen ball of stone, but a living, constantly changing organism. The continents we call home are but a temporary state, a fleeting snapshot in a cycle that lasts billions of years. Pangea was just one phase of that cycle, majestic but short-lived. Before it, there were other giants like Rodinia and Nuna, and after it, in the distant future, perhaps Pangea Proxima or some other supercontinent, unimaginable to us, will emerge. When the lands finally merged after millions of years of collisions and compressions, the resulting world was simultaneously familiar and utterly alien. Familiar because its vast expanses were filled with rustling forests, flowing rivers, and home to wondrous animals. And alien because its scale, its unity, had no parallel in the modern world. This long journey to Pangea forces us to wonder, what was that world like, united and vast, before its slow but inexorable disintegration began? When we imagine the world, a familiar map comes to mind. Continents with their recognizable shapes, oceans separating them, and a climate that seems the only possible one simply because we were born there. However, Earth has had a long history, and many of its ancient faces we would simply not recognize today. Long before Pangea, before the age of dinosaurs, mammals, and especially humans, there were lands and seas on the planet that would seem to us like landscapes from another planet. But they were as real and vibrant as our own. Every vanished supercontinent, every dried-up ocean, every ancient forest and deserted coastline were once entire worlds. Looking back at this distant past, we realize that the Earth we know is but one version, one page in the incredibly thick book of our planet's history. These ancient worldviews remind us of how changeable our planet is. Continents don't stand still. They are in perpetual motion. Oceans don't exist forever. They are born, expand, and die, giving way to land. Climate, too, is constantly changing, fluctuating from the icy cold of global ice ages to the scorching hell of greenhouse ages. Even the very air we breathe has undergone colossal changes, evolving from a toxic methane haze to an oxygen-rich atmosphere. What we see around us today is but a moment in geological eternity. The continents we know will drift again. Oceans will disappear and new ones will arise in their place. Climate will shift to extremes we can't even imagine. Earth has always been a dynamic planet, and it always will be. This thought may seem alarming. We've become accustomed to perceiving our world as the norm, as some natural and uniquely correct order of things. But this is merely an illusion. For most of Earth's history, there was no Atlantic Ocean, no Sahara Desert, no majestic Himalayas. In their place, there were ancient seas like the Iapetus and Tethys, towering mountains that have long since become nothing more than dust. And instead of oaks and pines, the planet was covered in forests of giant club mosses and tree ferns. What seems eternal to us is, in fact, only a moment in time. But the lessons we learn from these ancient worlds extend beyond geography. They tell us about life itself. Each cycle of supercontinent formation and breakup brought both destruction and incredible opportunity. Plate collisions uplifted mountains and closed seas, destroying familiar ecosystems. But at the same time, they created new landscapes where life had the chance to evolve in new directions. Global climate change drove some species to extinction, but opened up ecological niches for the emergence of new ones. The Great Oxygen Revolution nearly wiped out ancient anaerobic life, but it made possible the emergence of complex animals, including us. Earth's history proves again and again, change is not an accident, it is a fundamental requirement for life. Let's look at ancient forests. Their spread across the planet dramatically altered the atmosphere, absorbing vast amounts of carbon dioxide. Forests transformed the face of the Earth. They oxygenated the air, possibly triggering several ice ages, and created entirely new habitats for countless insects, amphibians, and reptiles. The world before forests was harsh and almost lifeless on land, but when they appeared, it was a true revolution. Or consider the oceans, which before the age of Pangea teemed with trilobites, anomalocaridids, straight-shelled cephalopods, and armored fishes. These amazing creatures are long gone, but they left an indelible mark on the history of life. Every extinct ecosystem was once a world unto itself for those who inhabited it. Ancient landscapes are also a monument to the incredible resilience of life. It has survived fire, water, and ice. Life has survived eras when glaciers covered the planet all the way to the equator, and it has endured greenhouse conditions when unbearable heat and fierce storms seemed eternal. Life has withstood asteroid impacts, supervolcanic eruptions capable of devastating entire continents, and mass extinctions that wiped out most life on Earth. And each time, after each catastrophe, life has found a way to regenerate. It has adapted, changed, and reinvented itself. We exist only thanks to this remarkable ability of our distant ancestors, microbes, plants, and animals, who found solutions to crises the scale of which we cannot even imagine. However, Earth's history also bears witness to fragility. Ecosystems that flourished for millions of years collapsed overnight when climate change occurred or oceans closed. Entire groups of organisms that once dominated the planet, such as trilobites, placoderms, and giant brachiopods, disappeared forever. The world has no obligation to preserve any particular form of life. Survival is not a right, but the result of adaptability. And even the most successful and powerful creatures can disappear if conditions change too quickly. If we could travel back in time and set foot on the soil of ancient continents, what would we feel? On a tiny protocontinent, we would see only bare rocks covered in thin films of microorganisms and hear a deafening, unearthly silence. And standing in the vastness of Rodinia, we could find ourselves in We walked through parched deserts under a foreign, unfamiliar sky and wandered along the shores of shallow seas long unmapped. We listened to the quiet lapping of waves lapping ancient shores and observed their primitive, very first inhabitants. We will be transported to those dense forests where the rustling of giant ferns mingled with the deafening hum of insects as large as modern hawks. In those days, the world was full of life, but at the same time, it held within itself some primordial, frightening secret. Our long journey to the great supercontinent of Pangea lay through endless, lifeless deserts, and then through the teeming swamps of the equatorial plains, where countless amphibians and the first clumsy reptiles lurked in the murky waters. Every corner of the ancient Earth possessed its own unique character, lived at its own pace, and breathed its own distinct atmosphere. And all these lost worlds, all these landscapes, were subject to one great and eternal cycle. Imagine this grand cosmic dance. Continents slowly converge into a single mass, then tectonic forces tear them apart, only to begin their movement toward each other again hundreds of millions of years later. Oceans are born and die. The planet's climate transforms it from an icy ball to a scorching tropic. Life blossoms in incredible diversity. Then great extinctions wipe it from the face of the Earth, only to rise like a phoenix from the ashes in new, even more bizarre forms. In this endless saga, there is no ending, no final chapter, only new turns of the spiral of time. Just as the mighty Pangea was eventually torn apart into the continents we know today, so too will our modern continents one day merge back into a single whole. Perhaps this new supercontinent will emerge in the middle of the Pacific Ocean, burying it beneath itself, or perhaps the Atlantic will close. We can't predict with certainty what form our planet will take, but one thing is certain: it will emerge, and Earth will have a completely new face. These reflections on the future are important not because any of us will live to see it. They are important because they force us to grasp the true scale of time. Our human lives are but a flash in the pan, and our civilizations are mere grains of sand against the backdrop of the geological eternity in which continents and oceans exist. And yet, we are part of this history. We walk on land that has witnessed all these incredible transformations. The very stone you might pick up on your walk today once rested at the bottom of a long-vanished sea. These majestic mountains that prop up the sky are nothing more than the scars of titanic collisions of continental plates in the distant, distant past. The very soil beneath our feet was formed from the ashes of ancient forests wiped off the face of the Earth millions of years ago. Every inch of this planet holds the memory of countless bygone eras. When you look at a familiar map of the world, it creates a dangerous illusion of stability and immutability. But look deeper, beneath this thin veneer of the present, and you see a world in constant, inexorable motion. Right now, the Atlantic Ocean is relentlessly expanding its borders, while the Pacific, conversely, is slowly dying, shrinking with each passing year. Africa is steadily creeping northward, destined to one day collide with Europe, while Australia continues its lonely drift. Every coastline, every border on this map is but a fleeting snapshot in the planet's long history. Those very continents whose names we memorize in school will look completely different in the distant future. They are merely a reflection of the present moment, a brief chapter in the Earth's annals. Even the sky above us, so familiar and eternal, was in fact constantly changing. Once it was painted a poisonous orange by a thick methane haze, beneath which life barely flickered. Then came the oxygen revolution, and for the first time in history, the sky turned a deep blue. Later, the ozone layer appeared, an invisible shield that filtered out the deadly radiation of space and allowed the first brave creatures to finally step onto dry land. Think about it. Even the air we breathe every second is not a given. It was created for us by the titanic labor of ancient forests and microscopic ocean dwellers. And this cycle will not stop. In the distant future, everything will once again change beyond recognition. To contemplate these lost worlds is to grasp a striking paradox. Our Earth is simultaneously incredibly fragile and utterly eternal, its appearance temporary yet unchanging. The planet's face is constantly changing, but its essence, its heart, remains the same. Life flows on it in a continuous stream, and its history is being written even now. You and I are but one page in this infinitely long book. another species of creatures, perfectly adapted to the conditions of our particular time. And perhaps this is the greatest lesson we learn from the distant past, the era that existed long before Pangea. It's not that that world was alien or strange, it's that change is the only constant. Earth has never been as we see it today, and it will not remain so for long. But in each of its new appearances, in each new era, we can discern incredible beauty, unwavering resilience, and the eternal miracle of life's origin. And so, after long and wondrous journeys through long-vanished corners of our planet, we return to our own time. We witnessed the drift of continents. We saw entire oceans born and die, and the skies above us change from a suffocating orange to a piercing blue, saturated with life-giving oxygen. We wandered among the first forests on the planet. Can you imagine it? Giant insects buzzing deafeningly as they darted through the shadows of tree ferns. We watched as individual landmasses slowly, centimeter by centimeter, coalesced into a single supercontinent, Pangea, watching this spectacle as if we were witnessing the arrival of cosmic giants. It was an incredible journey, capable of forever changing our view of our own lives. The ground beneath our feet, the air we breathe, and even our knowledge. All of this is but a moment in the continuous, eternal rhythm of the planet. If you've been with me this entire journey, from start to finish, I want to thank you sincerely. It's astonishing to realize that such a familiar and dear planet can be so fleeting. That every coastline we know is just a brief sketch, drawn in pencil on the sands of time, destined to be washed away by the next wave of change. But this transience is part of the great miracle. When you step outside tomorrow, stop for a moment. Look at the sky, touch the earth beneath your feet, listen to the whisper of the wind. All of this is more than just a backdrop to our lives. All of it holds within it pieces of a much deeper history, a history that is older than the most ancient forests, older than the first animals to crawl onto dry land, a history that is older than Pangea itself. And if you enjoyed this leisurely stroll through the abyss of time, if it brought you peace, sparked your curiosity, or even lulled you to sleep, know that you are always welcome to join me again. We still have so many unsolved mysteries to discuss, even more forgotten worlds awaiting exploration, and countless fragments of Earth's great history yet to be discovered, until we meet again. And wherever you are, whatever time of day you hear these words, just know, despite all the endless changes, the Earth continues to rotate, the continents continue their eternal drift, and the great story continues. Let's go back to a time when the planet didn't have the continents we're accustomed to, only giant landmasses, supercontinents. Imagine a world where the air was completely different. Our planet's very atmosphere was just undergoing the greatest transformation in its history. Tiny photosynthetic microbes, invisible to the eye, carried out titanic work, saturating the air with life-giving oxygen. Life in those eras was represented only by microscopic forms, but it was the great movement of tectonic plates that became its greatest ally. Continents, colliding and moving apart like giant paddles, stirred the waters of the world's oceans, distributing precious nutrients and thus setting the stage for the coming explosion of evolution. And if we look even further back in time, some 3 billion years ago, we might see the first recognizable giant in Earth's history, a continent named Ur. Compared to the mastodons that would come after it, it was a true dwarf. But there's a theory that its oldest fragments, like indestructible relics, survived all subsequent eras of collisions and disintegrations, and to this day they rest deep beneath our feet in the very foundations of the Earth's crust. The very idea that our planet had experienced countless cycles of the assembly and disintegration of giant continents long seemed utterly fantastic. For centuries, scientists were convinced that continents were eternal and immutable, forever locked in place. And even when, in 1912, a bold scientist named Alfred Wegener dared to suggest that the continents were drifting, his hypothesis was met with icy disbelief and ridicule by the scientific community. A breakthrough only came in the 1960s with a discovery that revolutionized everything. The process of seafloor spreading and the theory of plate tectonics finally made it possible to fit all the pieces of the puzzle together. In an instant, everything fell into place. It became clear that the famous Pangea was merely the latest act in a long, captivating drama of continental amalgamations. We're used to feeling the ground beneath our feet as a symbol of solidity and stability. But in reality, the continents are eternal wanderers, slowly circling the planet in their own majestic dance. They collide, merge, and then separate again, like partners in an endless geological waltz. And Pangea is just one frozen frame, a single moment in this grand dance. When researchers first pieced together the map of Pangea, they were amazed not only by the perfectly aligned coastlines, like pieces of a puzzle. On continents that are today separated by vast oceans, they discovered identical fossils and identical rocks. Remains of the same species of ancient reptiles and extinct plants have been found in South America and distant Africa. Titanic mountain ranges, today separated by thousands of kilometers of salt water, suddenly merged into a single continuous scar on the body of the ancient planet. Digging even deeper, we can find traces of much more ancient eras. Tiny magnetic minerals are hidden within rocks. At the moment of their formation, like compass needles, they become frozen forever, pointing to the Earth's magnetic poles of that time. By comparing these ancient magnetic maps from different continents, scientists were able to discern striking patterns. The ghostly outlines of long-vanished supercontinents began to emerge. It was this painstaking, detective work that allowed them to resurrect the silhouettes of Rodinia, Nuna, and Kenorland, the contours of lost worlds buried in the planet's geological record. But the real mystery isn't simply that the continents are moving, it's that their endless movement created the very conditions in which complex life could emerge and flourish. Consider this: without the crushing collisions of tectonic plates, majestic mountains would never have risen to the sky. And without mountains, there would be no erosion, which over millions of years leached nutrients from rocks and carried them into the oceans, fertilizing the cradle of life. If the oceans hadn't opened and closed, the planet's climate wouldn't have changed so dramatically, pushing evolution toward new solutions. It's safe to say that this restless, eternal dance of the continents is one of the key reasons why life on our planet has become so incredibly rich and diverse. We often think of Pangea as something completely unique, a one-of-a-kind event. But in reality, its formation was just one act in an endless geological symphony that, incidentally, continues to this day. The continents so familiar to us from school maps are still in flux. The Atlantic Ocean continues to slowly but inexorably expand, pushing North America further and further away from Europe and Africa. Meanwhile, the Pacific Ocean is gradually shrinking, its ancient seafloor sinking into the planet's depths. Millions of years will pass, and a new supercontinent will inevitably form on Earth, which scientists have already named Pangea Proxima. This will be the moment when today's disparate lands will once again come together as a unified whole. In other words, this gigantic planetary puzzle is never fully solved. Its pieces are constantly rearranged, creating ever new patterns. The story of Pangea isn't the tale of a single continent, it's the story of a repeating cycle of birth and death. The planet before Pangea wasn't an empty, featureless sphere. Other supercontinents had already been born and died on it, each with its own unique shape, climate, and fate, and each left behind deep traces that shaped everything that followed. If you learn to read these traces, you can see entire worlds that no human was destined to see, but which to this day shape the planet right beneath your feet. If you stare at a modern world map for long enough, it begins to seem almost alive. The continents no longer look like motionless blocks of stone. They seem frozen, momentarily, in the middle of their slow, majestic dance. South America seems still to reach for Africa, like a lost twin. Australia seems to be quietly trying to slip away from everyone, and frigid Antarctica stands frozen at the very bottom of the planet, like a lonely wanderer who has wandered too far south. The map we see is merely a snapshot in an endless film. Continents never rest. They glide slowly but steadily across the Earth's molten mantle for far longer than any known species has existed. We too easily forget this nomadic nature of our planet, and the reason is simple. Human life is but a blip in the backdrop of geological time. 100 years, 1,000, even 10,000 years for a continent, that's less than a second. You could sit on the shore of an ocean your entire life and notice absolutely no change. But over the course of millions of years, those same coastlines shift thousands of kilometers, stretch and vanish forever. Oceans are born and die. Mountain ranges rise to the heavens, crumble to dust, and reappear on the other side of the world. All of this happens so slowly that it completely eludes our perception. But for the planet itself, this movement never stops. Scientists call this monumental process plate tectonics. Today, it's taught in school, but when Alfred Wegener first proposed his idea of continental drift in the early 20th century, it was considered utter madness. The very idea that entire continents could slide across the surface of the globe like giant ice floes seemed like the stuff of science fiction. It wasn't until the 1960s, after the spreading of the ocean floor was discovered and mysterious magnetic patterns in the crust were studied, that his theory finally gained acceptance. And then, for the first time in history, humanity was able to tell the complete unified story of Earth's great voyages. But this story began long before Pangea. Before it, other supercontinents emerged and disappeared, leaving behind only encrypted messages in ancient rocks. If we could rewind Earth's history like an old film, we would see a stunning sight. The familiar contours of the continents would begin to merge into bizarre, unfamiliar shapes. Seas would disappear, transforming into mountain ranges, and entire continents would disintegrate into fragments unlike anything on modern maps. Continents are eternal wanderers, traveling incredibly long distances. Sometimes they drift apart, drifting alone across vast oceans, and sometimes they come together, forming colossal landmasses where they remain for millions of years. Each such collision leaves deep scars on the planet's surface. Ancient mountain ranges, nearly erased by time and wind, still preserve the memory of these ancient unions. For example, the Appalachian Mountains in North America share a common geological history with mountains in Scotland and Scandinavia. This is a silent reminder of the time when these lands were one, before the Atlantic Ocean opened between them. Clues are preserved even in tiny invisible minerals. Crystals within volcanic rocks, as they cool, align themselves along the Earth's magnetic field, forever recording their positions. Billions of years later, geologists can read these magnetic signatures, reconstructing the location and position of each continent. Thus, step by step, a map of the ancient Earth was reconstructed. The continents drifted from pole to equator and back, and their journey was filled with truly dramatic events. Take India, for example. 100 million years ago, it lay near the South Pole and was part of the gigantic continent of Gondwana. Then it broke away and rushed north at incredible speed, eventually smashing into Asia. This collision gave birth to the highest mountains on the planet, the Himalayas, and this colossal accident continues to this day. If you ever stand at the foot of Everest, know this. You will be standing on limestone that was once the seafloor of the ancient Tethys Ocean. Continents carry with them their own history. The stones beneath our feet could have traveled thousands of kilometers before ending up here. They could have been part of an ancient mountain range or the bottom of an ocean that disappeared from the face of the Earth millions of years ago. Each continent is a multi-layered book, a chronicle, rewritten many times by time and the movement of the planet. Before Pangea, there were Rodinia, Nuna, and Kenorland. Rodinia, which existed about 1 billion years ago, may have amalgamated almost all of the planet's landmass into a single gigantic mass. Its breakup approximately 750 million years ago triggered dramatic climate change and, according to scientists, caused a global glaciation, turning the Earth into an ice ball. Nuna, even older, united parts of modern-day North America, Scandinavia, and Australia, and Kenorland, which formed 2.7 billion years ago, existed on a young, hot, and almost unrecognizable planet. But it's important to understand not only that the continents moved, but how their wanderings shaped life itself. When continents coalesce, climates become extreme. The interiors of supercontinents become lifeless, sun-baked deserts. But when they break apart, new coastlines and shallow, warm seas emerge, ideal incubators for life to flourish. It could be said that the biosphere breathes in time with the movement of the continents, sometimes expanding, sometimes contracting with them. Even the chemistry of the oceans obeys this great rhythm. When plates collide, mountains rise into the sky. Erosion carries nutrients from them into the seas, triggering veritable explosions of biodiversity. And when continents drift apart, volcanic activity releases enormous volumes of carbon dioxide into the atmosphere, warming the climate. These global processes have caused both mass extinctions and new, unprecedented blooms of life, and it's worth remembering. Once upon a time, continents didn't exist at all. Billions of years ago, the Earth's crust was much thinner and hotter, and all land was made up of small, scattered fragments. The first continents were mere islands of stable crust in a vast global ocean. But over time, they grew, collided, merged, and transformed into the giants we speak of today. Thus, step by step, the planet transformed primordial chaos into order, and the restless movement of the land became the rhythm to which life itself danced. It wasn't just that continents shifted places. They, in fact, changed their identity. What began as a small proto-continent could only survive in fragments, joining larger landmasses, then breaking away again and merging with something new. The continents we know today are a complex mosaic, a patchwork quilt stitched together from dozens of ancient travelers of the past. If you could look at the Earth 3 billion years ago, you would see only volcanic islands scattered across the ocean, tiny specks of land just beginning their long journey. Imagine the vast ocean of early Earth. Its surface was devoid of the continents we know today, only scattered islands of land, like the first sketches of a future world poking through the water. Fast forward 1 billion years into the future, and we see these fragments coalescing to form the supercontinent of Kenorland. Another 1 billion years will pass, and it will be replaced by Nuna, then the mysterious Rodinia, and finally the famous Pangea. At each of these stages, the appearance of our planet changed beyond recognition. Earth has never known rest. It has always been in constant motion, and this great journey continues to this day. Right now, Africa is slowly but inexorably creeping northward, destined to collide with Europe. Australia is heading toward Asia. California, located on the Pacific Plate, is moving northwestward at a rate comparable to the growth of human fingernails, just a few centimeters per year. This may seem insignificant. But on the scale of geological time, over tens of millions of years, this movement is enough to reshape entire coastlines and raise new mountain ranges from the depths of the sea. The world map we know is just a single frame in a grand film that has been unfolding for billions of years. To look at Earth from this perspective is to realize that our planet is not a static stone, but a living, breathing organism, constantly changing its appearance. These wandering continents bear more than just rocks and mountains. They are the guardians of the entire history of climate and life. Every step they take across the abyss of time leaves a deep imprint, which shapes the world we inhabit today. And as we ponder these thoughts, it's important to remember, a new turn in this endless cycle awaits us. Millions of years from now, the continents will reassemble to form a new supercontinent. The great journey never ends. If Pangea is the supercontinent we know most about, Rodinia remains its mysterious shadow from the distant past. Its name is rarely heard outside geological circles, it is almost forgotten, but its significance to the planet's history is enormous. Rodinia existed over 1 billion years ago. This was a time long before animals appeared, before forests emerged, and even before living organisms learned to create their first shells and skeletons. Yet, it was this gigantic landmass that brought together almost all of Earth's continents, shaping the planet's appearance in a way that echoes to us today. The name Rodinia comes from the Russian word for motherland or homeland, and this is highly symbolic. After all, in a sense, it became the birthplace of those geological processes and global changes that set the stage for the emergence of future complex life. It formed approximately 1.1 billion years ago, at a time when Earth had already cooled enough to possess a stable crust. Rodinia became one of the largest and longest-lived continental agglomerations our world has ever seen. Of course, there were no witnesses to this grandeur. No animals, no trees, not even the sounds we are accustomed to. Only silent mountains, erupting volcanoes, shallow warm seas, and a sky tinged with the strange chemical hues of a young atmosphere that was just beginning to oxygenate. But how can we even know about Rodinia's existence if it was so ancient and lifeless? The answer is hidden in the rocks. All modern continents retain the most ancient fragments. Cratons. These are strong, stable cores of continental crust that have survived billions of years of tectonic upheavals. By studying their age, chemical composition, and the magnetic traces frozen within them, scientists can reconstruct the exact locations of these fragments in the past. By comparing data obtained in North America, Siberia, Australia, China, and other parts of the planet, they discovered a striking pattern. Around 1.1 billion years ago, all these disparate pieces came together to form a single puzzle, forming the landmass of Rodinia. However, unlike Pangea, the precise contours of Rodinia are extremely difficult to visualize. Scientists still fiercely debate its shape. According to some models, North America was at the center of this giant, surrounded by what would become South America, Africa, and Australia. Other reconstructions propose completely different configurations, with rotations and rearrangements of blocks. The problem is that over 1 billion years, the ancient rocks have undergone colossal changes. Countless collisions, erosion, and metamorphism have distorted the original evidence. Trying to reconstruct Rodinia's appearance is like assembling a gigantic painting from charred and torn fragments. But even among these fragments, there is enough evidence to confidently conclude it existed. Rodinia is significant not only for its very existence, but also for its timing. 1 billion years before its formation, Earth's atmosphere began to fill with oxygen, produced in vast quantities by microorganisms. This oxygen didn't just change the composition of the air, it transformed the chemistry of the oceans, making the planet potentially suitable for the development of complex life. When continents merge into a single entity, the planet's climate changes dramatically. The interior of the giant supercontinent becomes incredibly arid. Located thousands of kilometers from the oceans, they are virtually devoid of moisture. The center of Rodinia likely represented a gigantic lifeless desert, while shallow seas teeming with microbial mats stretched along its edges. Approximately 750 million years ago, Rodinia began to break apart. Massive tectonic forces tore it apart. New oceans were born, continents were free-floating, altering sea currents and the global climate. It was then that Earth may have entered one of the most extreme eras in its history, the Snowball Earth era, when glaciers covered the planet almost to the equator. Some scientists believe the planet froze completely, turning into an ice ball covered in kilometers of ice, save for rare warmth oases near volcanoes. Others believe that bands of open water still remained at the equator. Whatever the case, the breakup of Rodinia played a key role. It altered the balance of greenhouse gases, triggered massive ice ages, and essentially reset the planet's entire climate system. Imagine this world. A world without sound, without the movement of complex life. a world encased in ice. But even in this deafening silence, microbes continued to cling to life. And when the glaciers finally retreated, an entirely new era began, the era of complex multicellular organisms. The story of Rodinia is not only geology, but also biology. Its formation and subsequent disintegration created the very unique conditions that pushed life to a new stage of evolution. It is a stark reminder that continents are not simply passive scenes, but active participants in the great drama of existence. If Rodinia had not formed or disintegrated as it did, if climate shifts had been different, life on Earth might have taken a completely different, unpredictable path. Perhaps we would not even exist. Standing on the ocean shore today, gazing at the eternal surf and ancient cliffs, it's hard to comprehend the full depth of time. But that stone lying at your feet could have been part of Rodinia, a wandering fragment that survived a billion-year journey. Rodinia is called the Forgotten World, not because it's unimportant, but because its era is so distant that it's difficult to comprehend in the human imagination. We can imagine dinosaurs roaming Pangea because we've seen their skeletons. We can imagine the breakup of Pangea because we still see continents drifting today. But a billion years ago, when Rodinia ruled the planet, there were no familiar landmarks. It was a world of rock and microbes, a world shaped by colossal forces we rarely notice in our daily lives, yet which never cease to be at work. And just as Pangea once broke apart, so did Rodinia. Its fragments drifted apart, regrouped, and eventually formed new supercontinents, Gondwana and Laurentia. Each left an indelible mark on Earth's history. This cycle continues and will continue until the planet cools so much that its tectonic heart stops beating. Reflecting on Rodinia reminds us that Earth has had many faces. The world we know is but a moment in its incredibly long history. Continents will continue their wanderings, oceans will open and close, and climates will shift from warm to cold and back again. In this endless cycle, Rodinia was one of the forgotten yet pivotal actors in the great planetary drama. And as we leave behind this glimpse of the ancient world, the birthplace of the continents, it's logical to ask, what came before? What worlds existed before? What ancient supercontinents laid the foundation for its formation? Among them, Nuna, or Columbia, stands out, its even more ancient ancestor. This supercontinent emerged nearly 2 billion years ago, marking one of the first times Earth consolidated most of its landmass into a single colossal mass. Although the details of its history are blurred by time, traces of its existence can still be seen in the planet's oldest rocks. Imagine a world without a single tree, without animals, without shells on the beach, only slippery microbial mats lining the shores and single-celled life drifting passively through the oceans. Into this silent world arose a continent, comparable in scale to the greatest giants of geological history. The first of the titans that could be called a true supercontinent. The name Columbia arose because one of the first reconstructions placed North America at the center of this ancient landmass. Geologists often start with something familiar. Other scientists prefer the name Nuna, which means Earth in the Inuit language. Both names are used almost interchangeably, but the scale of the phenomenon is more important than the name. Columbia stretched across vast territories, encompassing what would become North America, Greenland, the Baltic, Siberia, India, Australia, and South America. The exact locations of these blocks are still a subject of scientific debate, but evidence suggests that approximately 1.85 billion years ago, they did indeed form a single landmass. Recreating such a distant past is an incredibly difficult task. Over this time, rocks have been repeatedly reshaped, compressed into folds, and uplifted to enormous heights. However, geologists are finding clues. Ancient mountain belts, preserved on different continents today, serve as markers of where land masses once collided. For example, the remains of ancient mountain systems in Canada are strikingly similar to those found in Greenland and Northern Europe. This is a sure hint that they were once a single entity. Another key is paleomagnetism, imprints of the Earth's magnetic field frozen forever in minerals. By comparing these ancient compasses across different continents, scientists can determine whether these lands were once adjacent. It is this data that helps delineate the approximate boundaries of Columbia. Life at that time consisted primarily of microbes, but it was the formation of Nuna that changed the planet forever. The collision of continents created gigantic mountains, and their subsequent erosion washed tons of nutrients into the oceans. This became a powerful stimulus for the growth of microorganisms, which in turn saturate the atmosphere with oxygen. It is believed that it was during the Nuna era that atmospheric oxygen levels reached new heights. Scientists sometimes call this period the boring billion, but this boredom was deceptive. Evolution proceeded slowly but steadily. The stage was set for the future Cambrian explosion, a frenzy of life, and along the edges of this supercontinent stretched endless shallow seas. Let's travel back billions of years into the past, to a world where the seas teemed with invisible microbial life. Let's imagine ourselves standing on the surface of Nuna, one of the first supercontinents. What picture does this reveal? It's a completely alien, dead world. Everywhere you look are endless, parched deserts, bare rocks scarred by time, and sparse, frozen lava fields left by ancient volcanoes. There's not a blade of grass here, not a hint of soil. The sky above looks different. The ancient sun shines dimmer than we're used to, and the air is almost devoid of life-giving oxygen. The atmosphere is only just beginning to acquire it. But look underwater, and we see a completely different picture. The oceans of that time are a veritable cauldron of life. Giant colonies of cyanobacteria carpet the shallow seabed, forming living carpets known as stromatolites. These were the planet's first giant factories, tirelessly producing the oxygen that would one day change the world forever. The climate on this gigantic landmass was harsh and unforgiving. Arid, lifeless deserts stretched deep within the continent, while microbial ecosystems thrived in warm, shallow seas along the coastlines. The planet breathed fire. Frequent and powerful volcanic eruptions released colossal volumes of gases into the atmosphere, directly influencing the weather. The average temperature on Earth was likely significantly higher than today, although there were occasional periods of relative coolness that brought temporary respite and stability to the planet. Hundreds of millions of years of geological drama went into the creation of this giant. Continents, like titans, clashed in mortal combat, colliding and merging, leaving deep scars on the planet's surface. Their traces can still be found today, billions of years later, in the most ancient rocks, in the Canadian Shield, the Amazon Craton, and in the heart of Siberia. For geologists, these stones are like pages of an ancient chronicle, from which they piece together a history long since lost to oblivion. But nothing lasts forever under this dim sun. About 1.5 billion years ago, the titanic bulk of Nuna began to shudder. Gigantic faults, rifts appeared, splitting the supercontinent. Water gushed into the cracks, giving birth to new oceans, and the fragments of the once united landmass once again set out on their solitary voyage, only to meet and reconvene hundreds of millions of years later in a new, unprecedented configuration. This great cycle, the birth and death of supercontinents, has become the central rhythm of our planet's geological life. Every hundreds of millions of years, the disparate lands are drawn together, collide in a fierce battle, and then separate again to begin their dance anew. Nuna was just the first chapter in this endless saga, and the reason for this perpetual motion is the inexorable force of plate tectonics. Imagine a gigantic conveyor belt. New crust is born at the bottom of the oceans, pushing against the old, forcing it into the fiery depths of the planet at subduction zones. It is these processes that ultimately close entire oceans and weld continents together. But the system cannot tolerate rest. Heat from the Earth's interior begins to accumulate beneath the supercontinent's enormous lid, like steam in a sealed boiler. Sooner or later, this heat causes the crust to crack and disintegrate. And so, the endless dance of creation and destruction, merging and fragmentation continues. Nuna's role in Earth's history is inestimable, and it extends far beyond pure geology. It was the stability of its vast platforms that allowed the atmosphere to accumulate enough oxygen for future complex life and temporarily stabilized the climate. This gave microbial worlds the chance to develop and thrive. More importantly, it was during that distant era that the richest deposits of minerals, iron and other metals, formed within Nuna's depths. Billions of years later, these deposits would form the foundation of our entire human civilization. These ancient geological cores, or cratons, still form the foundation of regions such as the Canadian Shield, the Kapvel Craton in South Africa, and the Pilbara Craton in Australia. Without these ancient foundations, later continents might never have developed a stable foundation for growth and development. One of the most striking aspects of the history of another ancient world, Kenorland, is how little we know for sure about it. We construct much of the picture in our imaginations based on indirect evidence. Because it existed in the unimaginably distant past, there is almost no direct evidence left. Over billions of years, these ancient rocks were crushed, melted, and ground to dust by the inexorable forces of geology. Over the centuries, wind and water obliterated them from the face of the Earth, and the heat of the Earth's interior transformed them into something entirely new, what scientists call metamorphic rock. What remains are mere pitiful fragments, shards of its former glory, scattered across the planet. Geologists have to work like real detectives. They piece together these disparate clues, trying to piece together a plausible picture of the past. Sometimes the pieces of the puzzle fit together perfectly, sometimes they don't, sparking scientific debates that can last for decades. But whatever the details, the overall picture is clear. Around 2.7 billion years ago, Earth had already managed to assemble its disparate lands into one of the first supercontinents in its history. And here we are, faced with the intriguing question of the great cycle of supercontinents. If Kenorland was one of the first, did it begin the geological rhythm that continues to this day? Or were there other, smaller protocontinents before it, which appeared and disappeared, leaving virtually no trace behind? We can only speculate about their existence. Some scientists suggest that even more ancient landmasses may have existed, even given tentative names like Valbara. These were tiny embryonic continents, predating even Kenorland. If so, then Kenorland was not the first step in this dance, but merely the first, which we can discern through the mists of time. The name itself, Kenorland, comes from the Kenorren orogeny, a monumental mountain-building event whose traces are forever frozen in Canadian rock. These rocks were once part of that same supercontinent. This name is a perpetual reminder that all our knowledge is built on tiny fragments, on those rare places where ancient geology has survived to tell us its story. Most of the rest of that legacy is irretrievably lost, swallowed by the Earth's seething mantle and erased from the planet's memory. And yet, even from this meager data, we can judge the colossal importance of Kenorland. It was a pioneering land, one of the first truly global land masses. It witnessed the Great Oxidation Revolution, survived one of the earliest ice ages, and served as the foundation for the very cratons that underlie today's continents. Without it, the entire subsequent history of Earth would have taken a completely different course. Trying to comprehend the existence of Kenorland stretches our perception of time to its very limits. 2.7 billion years ago isn't just a long time ago, it's a figure almost impossible to comprehend. The entire history of humanity is just a few paltry thousand years. Even the age of the dinosaurs, which lasted nearly 230 million years, seems like a blink of an eye compared to this. Kenorland is more than 10 times older. This era is so distant from us that it seems almost mythical, and perhaps that's precisely why the name is so fitting. It reminds us that the history of our planet is far deeper, more complex, and more mysterious than we can imagine. When Kenorland finally fell victim to the inexorable cycle, its fragments scattered across the planet to give rise to the next giant, Nuna. The great cycle of continents assembling and disintegrating continued. This journey never ends, and each step lays the foundation for the next. From Kenorland, we can travel even further back in time, to even more ancient and fragile protocontinents, like the place where the very first continental crust may have formed. These were tiny islands of land destined to become the progenitors of the giants we know today. Long before Kenorland, Nuna, Rodinia, and, of course, the famous Pangea, a tiny, almost mythical continent, may have existed. Geologists have named it which means first or beginning in many ancient languages. It appears to be the earliest protocontinent we can confidently identify in Earth's geological record. Unlike its gigantic descendants, which occupied vast expanses, was incredibly modest. Its area may have been as little as a quarter the size of modern-day Africa. But despite its size, it played a far more significant role in the planet's history. After all, it likely became the seed from which all future continents grew. To imagine that era, we need to leap back almost 3 billion years to the Archean era. By then, Earth had already existed for about 1.5 billion years, but it remained a restless, fiery world. Its mantle was much hotter than it is today, its crust thinner, and volcanic activity prodigious. Oceans covered much of the surface, steam billowing above them in the light of a dim, young sun. Land was a true rarity, fragmented, unstable, constantly consumed and remelted in the fiery depths. In such hellish conditions, the emergence of a piece of crust, thick and strong enough to survive, was a true miracle. And may have been one of the first such lucky ones. We don't have a map of it, but we have something even greater: the oldest rocks preserved in the hearts of modern continents. They are found in South Africa, Australia, India, and Madagascar. These rocks are over 3 billion years old. They miraculously survived all the cataclysms, avoided remelting in the mantle, and still lie at the base of our continents. By comparing their age, chemical composition, and ancient magnetic fields, geologists have concluded that all these fragments were once part of a single whole. What did this world look like? Nothing like what we're used to. No forests, no animals, not even moss covering the rocks. The land was completely barren, its surface nothing but bare rock, covered with a thin film of microbes. The seas were already home to single-celled organisms like cyanobacteria, which slowly but surely saturated the world with oxygen. But the atmosphere was still toxic, oxygen-poor, and saturated with methane and carbon dioxide. The sky likely had a cloudy orange tint, and the climate fluctuated between extremes, driven by volcanic activity. Although was tiny, its significance for the planet was enormous. It was likely the first continent to withstand the destructive forces of early tectonics. It became the core to which other landmasses later began to be drawn, like a magnet, forming the future supercontinents: Kenorland, Nuna, Rodinia, and Pangea. Can be compared to a tiny crystal, around which the rest of the land gradually grew. Just consider how astonishing its very survival is. The Earth's surface is constantly in flux and reworking. Oceanic crust is born and completely disappears into the depths every few 100 million years. Continental crust is much thicker and stronger, so it lasts longer. But on the early, hot Earth, even this was unstable. But stood firm, and the fact that its fragments still rest in the hearts of modern continents is the greatest testament to its incredible resilience. This geological history is inextricably linked to the history of life. The shallow seas along the coast of could have become an ideal cradle for microbial mats, sheltered from the storms of the open ocean. The weathering of rocks saturated the water with nutrients, feeding the microbes, which in turn released oxygen, slowly but irreversibly changing the composition of the atmosphere. And although the emergence of breathable air was still hundreds of millions of years away, the process had already begun. scientists still debate whether was truly the first continent or simply the first whose traces we could find and recognize. Perhaps there were other, even smaller islands of land before it, which left no traces. Hypothetical names like Valbara are sometimes invented for them. But for now, this remains pure speculation. The history of however, is supported by facts. Its fragments are more recognizable and their age is better dated, allowing us to peer into the deepest mysteries of the birth of our world. Here, in the deepest antiquity, we can find traces of the first truly ancient landmass. It was likely not the only one in the primeval ocean, but its legacy proved so resilient that it has stood the test of time, surviving billions of years of violent geological cataclysms. When we look at a modern world map, familiar silhouettes appear: mighty Africa, vast Asia, and the two Americas. But this is only the visible part of the picture. If we peer deeper into the very geological heart of these lands, we discover something incredible: fragments of ancient platforms, so-called cratons. Imagine the Capwell craton, the impenetrable foundation of southern Africa, stable and unimaginably old. And on the other side of the world, at the base of Australia, lies its contemporary, the Pilbara craton, just as ancient and monolithic. These are not just clusters of old rocks. These are genuine relics, fragments of the very first land on our planet, which somehow miraculously survived through the abyss of time. When a person sets foot on this land, they literally touch the dawn of Earth's history. These fragments are what amaze scientists, demonstrating the great continuity of planetary cycles. Continents are born, break apart, drift, collide, and merge again. Each new giant continent is essentially built on the ruins of its predecessor. This great discovery once became the key to understanding all of geological history. Just think, that very first continent became the foundation for the next, known as Kenorland. From the ruins of Kenorland, Nuna arose. And then, from the pieces of Nuna, Rodinia came together, which, in turn, became the basis for the famous Pangea. Each subsequent supercontinent carries within its structure the genetic code of its ancestors, stitched together into entirely new, bizarre patterns. And even today, as the continents continue their slow drift toward future epic collisions, the ancient heart of the first continent, still beats, hidden deep within the Earth's depths, yet remaining an invisible link in the great mosaic of the Earth. There's something breathtaking about this realization. We modern researchers can only glimpse this abyss of time, relying on scattered clues. The ancient rocks that have survived to this day are often unrecognizably altered by monstrous heat and pressure, transformed into entirely new mineral forms. And yet, within them, isotopic traces of hoary antiquity remain, crystals bearing the imprint of primordial conditions, and magnetic particles that still point to the latitudes where they once formed. Deciphering the messages of these stones is like trying to hear a quiet whisper, reaching us across a chasm of billions of years. This work requires incredible patience, scientific imagination, and a willingness to embrace inevitable uncertainty. And yet, the very fact that we are able to detect this ancient whisper is truly astonishing. If we could travel back in time and see the Earth with our own eyes, it would appear desolate and perhaps even boring, a mere cluster of barren, rocky lands washed by endless, lifeless oceans. But it was precisely in this pristine simplicity that lay its future greatness. Without these first islands of land, stable platforms on which life could establish itself and thrive would likely never have emerged. Without the shallow seas that framed them, there would have been far fewer microbial ecosystems, and therefore precious oxygen would have entered the atmosphere much more slowly. Without this primordial scene, life as we know it might never have had a chance. So, although this first landmass was tiny, devoid of forests and animals, it became the quiet but confident beginning of the continents we walk on today. Its fragments survive to this day, silent guardians of the history of Earth's first geological experiment in creating a solid surface. In subsequent eras, the continents grew ever more massive, the planet's climate became ever more complex, and life became ever more widespread. The great cycle of assembly and disintegration repeated itself again and again, gathering the ancient fragments into Kenorland, then Nuna, then Rodinia, Pangea, and other as yet unnamed worlds, and each new continent bore the imprint of that very first tiny landmass from which it all began. Looking at a modern globe, one gets the deceptive feeling that the continents are eternal. Africa seems immovable, South America absolutely motionless, Asia vast and monolithic. But beneath this illusion of stability lies a startling truth, one that geologists have only been able to grasp in the last century. On the surface of our planet, absolutely nothing is permanent. Continents are in perpetual motion, oceans are born and die, and over hundreds of millions of years, continents converge only to break apart again. This relentless cosmic rhythm is known as the supercontinent cycle, one of the most fundamental natural processes on Earth. To understand this mechanism, imagine our planet as a giant egg, its shell covered in a network of cracks. These cracks are nothing more than the boundaries of tectonic plates. The plates themselves, these colossal fragments of the Earth's crust, do not stand still. They slowly but inexorably drift across the surface of the viscous, hot mantle, like giant ice flows in an ocean of magma. Along mid-ocean ridges, new crust erupts from the depths, pushing aside the old, and at subduction zones, ancient crust sinks back into the mantle to be remelted. This balance of birth and death maintains perpetual motion on the planet's surface. The continents, being part of these plates, travel alongside them like enormous rafts carried by a powerful and invisible current. Over tens and hundreds of millions of years, the map of our world changes beyond recognition. Sometimes continents are scattered across the planet, separated by thousands of kilometers of ocean. Other times, they collide in a titanic clash, forming a single colossal landmass, a supercontinent. This entire monumental process resembles the slow, powerful beating of the planet's heart. Supercontinents are born, live out their long geological lives, then break apart, only to reassemble hundreds of millions of years later in a new configuration. Pangea is the most famous of these giants, but it was far from the first and certainly not the last. Before it, there were Rodinia, Nuna, Kenorland, and possibly even older land masses like Valbara. Each had its own life cycle, its own unique history, and its own geological legacy. The interval between the formation of one supercontinent and the next typically ranges from 400 to 600 million years. Over the 4.5 billion years of Earth's history, there have been several such cycles. The reason for this eternal dance lies in the very nature of plate tectonics. When a supercontinent forms, it covers a huge swath of the mantle, acting like a giant thermal blanket. It traps the heat emanating from the planet's interior. Over time, this accumulated heat weakens the continental crust from within, causing gigantic rifts, and eventually the supercontinent breaks apart. New oceans open, and the continents begin their long drift. On the opposite side of the planet, the old oceans, conversely, begin to close, drawing the disparate landmasses back together. Thus, after hundreds of millions of years, a new supercontinent forms. This eternal rhythm influences more than just geography. It shapes the climate, governs ocean currents, and even directs the evolution of life. When continents merge, their interiors become arid deserts, cut off from the moisture of the seas. When they drift apart, vast shallow shelves emerge, ideal cradles for the emergence of new life forms. The breakup of the supercontinent Rodinia, for example, may have triggered the global glaciation known as Snowball Earth, and the formation of Pangea radically altered all existing ecosystems. Every collision of continents creates new mountain ranges. Today's Himalayas are the result of the collision of India and Asia, but during the supercontinent era, ranges thousands of kilometers long arose. Over time, these mountains were eroded away, feeding the oceans with nutrients and influencing the composition of the atmosphere. Thus, the supercontinent cycle links geology, biology, and climate into a complex feedback system that writes the history of our planet. If we could watch Earth in fast motion, with 1 billion years passing in minutes, we would see a mesmerizing picture. Continents swirl in an endless dance, colliding, merging, and then drifting apart again. It's a grand rhythm, with no conductor, governed only by the fundamental laws of physics on our planet. Evidence of this cycle comes from many sources. Paleomagnetism, which reveals the latitudes of ancient rocks, overlapping mountain ranges on different continents, identical fossils and rock types found on opposite sides of oceans. And radiometric dating allows us to determine the age of these events with astonishing accuracy. All these threads weave into a single grand story, the story of Earth's eternal breath, and this cycle is far from over. Right now, the Atlantic Ocean continues to expand, while the Pacific Ocean, conversely, is slowly contracting. Geological models predict that in 200, perhaps even 300 million years, a new supercontinent will emerge on Earth. It has already been named Pangea Proxima. Where exactly it will gather, in the current location of the Pacific Ocean or the Atlantic, is still a matter of scientific debate, but one thing is certain: the Earth's rhythm will not stop. Reflecting on this great cycle puts humanity in perspective. Our civilizations exist for thousands of years, our species for millions of years, but continents live in the rhythm of hundreds of millions of years. When ancient humans carved their first images into rocks, the continents were already practically where they stand today. When dinosaurs roamed Pangea, its parts were just beginning to drift apart. And when the first multicellular organisms appeared in the oceans, the supercontinent Rodinia had already been torn apart. Our entire history is but a brief moment in this gigantic geological cycle. Some scientists wonder, what role does this cycle play in the long-term habitability of Earth? The constant recycling of the Earth's crust through collisions and faults helps regulate atmospheric carbon dioxide levels, maintaining a livable climate. Without this mechanism, greenhouse gases could either accumulate uncontrollably, turning Earth into a hellish furnace, or, conversely, the planet could freeze forever. In this sense, the rotation of supercontinents may be one of the key reasons why Earth has remained livable for billions of years, unlike lifeless Mars or scorching Venus. Studying this cycle helps geologists predict where valuable mineral resources may lie. Many of the richest deposits formed during the collisions and fractures of supercontinents in zones of intense tectonic activity. Therefore, understanding the timing and mechanics of this cycle is not just academic curiosity, but knowledge with practical benefits for our society. But perhaps the most striking thing about this cycle is its absolute inevitability. The continents don't choose whether to move closer together or further apart. They are driven by blind, powerful forces hidden deep beneath the surface. The mantle convects, the plates move, and the cycle continues. It is as integral a part of our planet as its rotation around the sun or the cycle of day and night. We live within this endless movement. This dance has been going on for billions of years and will continue for billions more. When looking at a map of the world, it's easy to see only what exists now, but behind this static image lies what was and what will be. The continents, we know, are merely temporary configurations, individual chapters in an incredibly long book. And the cycle of supercontinents is the book itself, its recurring plot, linking all the chapters into a single narrative. Following this rhythm through the ages, we begin to think not only about the land itself, but also about the oceans it shaped, the climates it created, and the entire worlds of living beings that arose and vanished forever within its vastness. When we talk about the movement and collision of continents, it's easy to focus on the landmasses, those giant pieces of the geological puzzle constantly being rebuilt. But for most of Earth's history, the oceans were the true center stage. Long before the first forests and animals appeared on the planet, long before. Before the familiar continental contours began to emerge, the oceans reigned supreme. They were the true cradle of life, the global thermostat that dictated climate, and a vast aquatic world that covered almost the entire surface of the Earth. To peer into the past, to the era before the emergence of the supercontinent Pangea, we must engage our imagination. We must see not just drifting land masses, but the gigantic oceans that stretched between them, for they were the primary force shaping every aspect of our planet's history. Today, water covers about 70% of the Earth's surface, but in ancient times, this figure was likely even greater. The continents were smaller, scattered across the planet like islands in a vast sea. They sometimes converged to form gigantic land masses, then broke apart again, but always remained at the mercy of the water. And these ancient oceans were not static. They were born and died in the eternal dance of tectonic plates. Where continents collided, an ancient sea contracted and disappeared, and elsewhere where the plates diverged, a new ocean basin was born from the fiery depths of the Earth. The entire annals of our planet are written on the bottom of these vanished seas. And although we will never see them again, their imprints remain forever in the rocks lying deep beneath our feet. One such oceanic giant of the past was named Iapetus. Imagine this. Approximately 600 million years ago, the Earth's crust began to crack and pull apart, creating a vast new water basin between what would become North America, Europe, and parts of South America. For millions of years, this ocean expanded, becoming home to a stunning diversity of early marine creatures, bizarre trilobites, all manner of mollusks, and the very first, still clumsy fish. But its time was up, when the continents once again came together in a deadly embrace. Forming Pangea, Iapetus was doomed. It closed, and mountains rose up in the place where it died. Today, the Appalachian Mountains in North America and the Caledonian Mountains in Europe are nothing more than gigantic scars on the planet, reminders of the former grandeur of an ocean that no longer exists. But Iapetus was far from the first. Before it, there were other oceans, whose names ring like the music of ancient legends. Merovia, Panthalassa, Tethys, each witnessed its own era, its own unique configuration of continents. 1 billion years ago, the Merovia Ocean surrounded the supercontinent Rodinia, constituting a virtually unified global ocean. Later, the gigantic Panthalassa washed the shores of Pangea, occupying almost 3/4 of the globe, and the Tethys Ocean long separated the southern continent of Gondwana from the northern continent of Laurasia, until it disappeared, leaving behind only the modern Mediterranean Sea. Each of these water worlds experienced its own life cycle. They emerged, flourished for hundreds of millions of years, and then shrank and disappeared as the continents collided in yet another tectonic collision. Let's transport ourselves for a moment to the shore of one of these long-vanished seas. The sound of the surf crashing against the rocks seems painfully familiar. But that's where the similarities end. Everything around us is utterly alien. The air is thicker and smells different. The sky above has an unfamiliar hue. And most strikingly, there isn't a single blade of grass or tree on the shore. Life hasn't yet dared to step out of the water onto dry land. It's all concentrated there, in the depths. Slippery microbial mats sway in the shallows, and stromatolite reefs built by billions of bacteria rise. And deep below, strange creatures live, encased in shells and possessing limbs unlike anything we know today. The oceans were the primary controllers of climate on ancient Earth. Their currents, like gigantic rivers, carried heat from the scorching equator to the cold poles, distributing energy evenly across the planet. When supercontinents formed, these global flows were disrupted. The climatic balance collapsed. When continents broke apart, new ocean currents emerged. Such changes could trigger severe ice ages or, conversely, periods of unbearable heat, creating new challenges for life that became a powerful driver of evolution. The chemical composition of the water was also never constant. Mighty mountain ranges were eroded by wind and rain, and rivers carried tons of minerals into the seas, changing their salinity and nutrient content. Volcanic eruptions released gases into the atmosphere, which dissolved in the water and affected its acidity. Oxygen levels fluctuated, sometimes leading to catastrophic mass extinctions of marine life. And yet, the delicate balance of carbon between the ocean and the atmosphere kept our planet within the habitable zone for billions of years. The greatest breakthroughs in the history of life occurred in the ocean depths. The first multicellular organisms appeared here around 600 million years ago. Then, approximately 540 million years ago, the so-called Cambrian explosion occurred, an evolutionary explosion that filled the seas with an incredible diversity of creatures with shells, spines, and the first eyes in history. Fish, our distant ancestors, also originated in the ocean. And only thanks to millions of years of marine evolution were their descendants able to eventually make their way onto land. It's no exaggeration to say that the oceans ruled the early Earth. They were the stage for all key events. We're accustomed to the Atlantic, Pacific, and Indian Oceans, but that's just the modern balance of power. Before them, there were Panthalassa, Tethys, Iapetus, Merovia, and dozens of others whose names are lost to time. Each of them existed for hundreds of millions of years, more than enough time for entire ecosystems to emerge, flourish, and vanish forever. Their legacy lives on today, in the folded rocks of the Himalayas and the Alps, in layers of marine sediment, and in the trilobite fossils that paleontologists find on mountaintops thousands of kilometers from the nearest sea. Ancient oceans were far more turbulent than we can imagine. Water levels fluctuated constantly, sometimes rising, inundating vast territories, then rapidly falling. At times, entire continents were submerged, becoming archipelagos in shallow inland seas. Then the waters retreated, leaving behind vast coastal plains. During the Ordovician period, for example, much of what is now North America was covered by warm, shallow seas where the first coral reefs flourished. Later, during the Cretaceous period, high sea levels split the continent in two, creating a vast inland sea. These cycles of water advance and retreat, which geologists call transgressions and regressions, continually created new conditions for life and steered evolution along new, unpredictable paths. When we consider these oceans, which existed long before Pangea, our perception of the world changes. We realize that everything that seems eternal is, in fact, only a moment. The continents on which we live are merely a temporary configuration. The seas on which our ships navigate are but a brief episode in an endless play. All of these are part of the eternal cycle of birth and destruction. And the oceans, perhaps, best reflect this restless, ever-changing nature of the Earth. They are born when continents drift apart, live through entire geological epochs, and then die when continents collide again. And yet, in their mutability, they are eternal. Oceans have always existed on Earth. They may be different, but water as such has never disappeared. In studying these oceans of the past, we're not just looking at water, we're peering into the face of time itself. Each vanished sea is a memory of an entire world that once existed on our planet, a world with its own shores, currents, and wondrous inhabitants. And it was from these ancient seas that life once took its boldest step, emerging onto dry land, looking up at the sky for the first time, and perhaps wondering for the first time where it came from. And so, from the dominion of the seas, we are transported higher into the skies above them, into the strange alien atmosphere that enveloped the Earth long before Pangea, back when the very air was poisonous to all life. When we try to imagine our planet's past, we most often think of land and sea. They seem material, tangible. But an equally important part of this world was air, and the sky above ancient Earth was nothing like the one we're accustomed to. Blue, with white clouds and life-giving oxygen. Its composition, density, and even color changed dramatically over billions of years. If we could travel through time, the air would feel completely different in different eras. Sometimes it would be deadly poisonous, sometimes thick and foggy, and sometimes so thin as to be unbreathable. The atmosphere was a key player in the fate of the planet. It shaped the climate, guided evolution, and ultimately decided whether life could survive. The very first atmosphere, more than 4 billion years ago, was completely unrecognizable. When the young Earth cooled slightly and was able to retain gases with its gravity, its sky filled with hydrogen and helium, the lightest elements in the universe. But the planet's gravity was still too weak, and these gases quickly escaped into space. They were replaced by a second atmosphere, born from the fiery breath of volcanoes. It was a hellish mixture of water vapor, carbon dioxide, methane, ammonia, and nitrogen, thick, foggy, and utterly hostile to life like ours. It contained virtually no oxygen, but it did contain enormous amounts of methane, a powerful greenhouse gas that traps heat far more effectively than carbon dioxide. This is perhaps what saved our planet. In those distant times, the young sun's light was much weaker than it is today. Without a powerful greenhouse effect, Earth would inevitably have turned into an ice ball. But thanks to the methane blanket, the surface temperature remained high enough for liquid water to exist. And it was in these warm waters that the first life emerged, simple, microscopic life that didn't require oxygen. Moreover, for many of these ancient organisms, oxygen was a deadly poison. Some even produced methane themselves, further enhancing the greenhouse effect and helping the planet retain heat. It was a fragile, yet surprisingly effective balance between the atmosphere and the first biosphere. And then something happened that changed the course of history forever. A true biological revolution. About 2.5 billion years ago, tiny organisms called cyanobacteria made an incredible evolutionary breakthrough. They learned to harness the energy of sunlight through photosynthesis. Absorbing water and carbon dioxide, they began releasing a byproduct, oxygen. At first, this gas dissolved in the oceans, where it immediately reacted with dissolved iron, causing it to rust and settle to the seafloor. This is how the famous banded iron ores we mine today were formed. But soon, the oceans became oversaturated with oxygen, and it began escaping into the atmosphere. This event, known as the Great Oxygenation Catastrophe, forever changed the face of our skies. Oxygen reacted with methane and destroyed it. The greenhouse effect weakened sharply, and the planet plunged into global cooling. Severe ice ages followed, with ice possibly covering even the tropics. For ancient anaerobic microbes, this was a true apocalypse. But for future complex life, it was the beginning of a new era. It was oxygen that enabled the emergence of organisms with more efficient metabolisms and complex body structures. And, although the emergence of multicellular animals was still a long way off, the foundation for their future prosperity had been laid. Along with the air, the sky itself changed. Before this turning point, it was likely painted in murky, reddish-orange hues, something similar to what we see today on Saturn's moon Titan. But as oxygen filled the atmosphere, it became increasingly transparent, and for the first time, the planet was graced by the piercing blue sky we know today. This transition took millions of years, and only by the end of the Proterozoic did the air begin to resemble what we see today. Even then, its composition continued to change. The level of oxygen in the planet's atmosphere, however, was like a restless heartbeat. It was not constant. Over the eons, it would soar and plummet, experiencing long periods of calm. Consider, for example, the so-called boring billion, a full billion years when life on the planet seemed to stand still, existing but making little evolutionary progress. Only much later, during the Ediacaran and Cambrian periods, did oxygen levels reach consistently high levels. This was the impetus that allowed complex animal forms to flourish in all their diversity. And throughout this endless period, the planet's mighty forces, volcanoes, tectonic shifts, and even asteroid impacts continued to sculpt and reshape the atmosphere. They sometimes turned the Earth into a scorching greenhouse, sometimes plunged it into an icy embrace. And above all this turbulent drama, nitrogen reigned like a silent giant, a quiet, invisible, and unchanging backdrop. it formed the very foundation of the atmosphere, creating the pressure and stability without which life would be unthinkable. Thus, step by step, our planet's sky became what we see, not in an instant, but as a result of billions of years of complex chemical and biological transformations. There was another enemy that made the ancient sky deadly: harsh ultraviolet radiation. Until oxygen accumulated in the atmosphere and the ozone layer formed, Earth simply had no protection. The sun's deadly rays pierced the thin atmosphere unimpeded, literally scorching the planet's surface. Therefore, all early life was forced to hide in the ocean depths, beneath the protective layer of water, or to huddle in shadowy underwater crevices. And only when this invisible ozone shield spread over the planet did life finally gain access to land, its protection from the deadly rays of space. The sky itself, having acquired this thin layer of ozone, became a powerful guardian, forever changing the rules of the game and opening the way for all the future diversity of life. We've become so accustomed to our sky that it seems as if it's always been like this: a calm blue dome by day and a bottomless scattering of stars at night. But if we were transported back in time, the sky of ancient Earth would seem completely alien and hostile. Imagine a thick methane haze, the acrid smell of volcanic gases in the air, and wild climate swings. From the bone-chilling cold of global glaciation to the stifling heat of the greenhouse effect. When atmospheric carbon dioxide concentrations soared to unbearable levels, the air became a constantly seething cauldron, and life was forced to either desperately adapt or change the world in response. This is one of the most striking qualities of the Earth's atmosphere. It was never simply a passive envelope of gases. It was always an active participant in the drama of life. Living organisms produced gases that changed the composition of the sky, and the sky, in turn, dictated which life forms would survive and thrive on the planet. The Great Oxidation Event was the most dramatic example of this interaction, but later eras also demonstrate the same inextricable connection. For example, when the first true forests appeared on the planet in the Devonian period, they began voraciously absorbing carbon dioxide and releasing oxygen. This not only changed the climate, but also cleared the way for the evolution of new animal groups. Sky and life were intertwined in an eternal dance, a continuous feedback loop. Let's transport ourselves there for a moment, beneath the vaults of that ancient sky. It's like finding ourselves on a strange alien planet, which, by some misunderstanding, is called Earth. Try to breathe the air of the Archean era, and you won't be able to draw a single breath, for it is toxic and devoid of oxygen. Find yourself here during the Great Ice Age, and the icy cold of a planet encased in ice will pierce you to the bone. And only if you were able to look up at the sky during the Cambrian period would you finally see something familiar, the familiar azure blue. But even then, the world at your feet would be utterly alien, inhabited by creatures from nightmares. The ancient sky is a powerful reminder that our planet never stands still. Even the very air we breathe every second has its own long and dramatic history. The next time you look up at the color of the sky or the drifting clouds, just remember: what you see is the result of a grand saga spanning billions of years. This is the sky, shaped by volcanoes and microbes, asteroids and ancient forests. It is a living witness to the great evolution of our planet. Studying this history, our gaze involuntarily descends from the heavens to the earth. To where the first living organisms began their perilous journey, leaving the ocean and colonizing land. For billions of years, the ocean was everything to life: a cradle, a climate regulator, and a gigantic natural laboratory where evolution conducted its boldest experiments. Meanwhile, the continents remained dead and deserted. Enormous waves crashed against silent, barren shores. Winds howled over lifeless cliffs, and rivers carved their way through landscapes devoid of a single plant capable of holding the soil. Land existed, but it was dead. But gradually, this picture began to change. And so, slowly but inexorably, life began its great exodus from the ocean. But forget those images of brave fish with their first clumsy legs crawling out onto the sand. No, they weren't the first to colonize land. It was the most humble and inconspicuous of all living things: microbes. First came thin mats of cells growing on damp stones at the water's edge. And then came the first plants, most similar to modern mosses, low-growing, unpretentious, and incredibly resilient to the harsh conditions of the New World. And this world was truly hostile. Sunlight was merciless, scorching all life on the surface. Ultraviolet radiation was deadly. Water was desperately scarce. Days were unbearably hot, nights icy, and the air constantly oscillated between parching dryness and torrential rains. But the microbes did not give up, did not give. Their ancient traces are found in rocks over 1 billion years old, microscopic structures remarkably similar to modern stromatolites. They created thin, slimy mats that clung to rocks and, like a sponge, retained precious moisture. These microbial communities became the first ecosystems in history to arise at the boundary between sea and land. And within their tiny cells, photosynthesis was already in full swing. The very mechanism that once revolutionized the fate of the entire atmosphere was now helping them conquer a new, inhospitable world. Around 470 million years ago, the first true plants, the ancestors of modern mosses and liverworts, emerged. They were incredibly primitive, no roots, no leaves, but they already knew how to cling to rocks and nascent soil, and their tissues had learned to resist desiccation. Special waxy coverings, reproduction through spores, and the ability to absorb moisture directly from the air. All this arsenal helped them survive in places that seemed impossible. These first green carpets, spreading along rivers and seashores, marked a true turning point in the planet's history. For the first time in billions of years, land ceased to be completely barren. Gradually, plants began to transform the landscape. They retained precipitation, creating the world's first soils. They absorbed carbon dioxide and exhaled oxygen, forming entirely new ecosystems. Their primitive root systems and dying tissues created a breeding ground for microbes and fungi, which soon formed a strong alliance, symbiosis. The fungi helped the plants extract minerals from rocks, and the plants shared carbohydrates obtained from the sun. This partnership became the key to conquering the harsh world of early Earth. Even these tiny plants had a truly colossal impact on the planet. They accelerated the weathering of rocks, which led to a decrease in atmospheric carbon dioxide levels and, scientists believe, may even have triggered periods of global cooling. Their decaying remains enriched the soil with organic matter, literally preparing the ground for the arrival of larger, more complex plants. Rivers began to behave differently. Landscapes became stable, and water began to circulate across the continents in entirely new ways. And all this was thanks to living creatures just a few centimeters tall. Try to imagine this world: rocky shores beneath a strange, unfamiliar sky. The tide washes over slippery microbial carpets, shimmering in the sun. And in the distance, among the grey stones, the first green patches of moss appear. There are no trees, no grass, no flowers here. The air smells not of fields, but of dampness and wet stone. Almost complete silence reigns, broken only by the whistle of the wind and the lapping of the waves. And yet, it is here, before our very eyes, that life takes its first tentative steps on dry land. At first, these pioneering plants were alone, but very soon the first animals followed: primitive centipedes, sea scorpions, and ancient wingless insects. They arrived on land later, only after plants had already transformed the world, preparing a foothold for them. These first mosses and microbes were true pioneers, tiny yet capable of transforming the entire planet. We often imagine great revolutions in the history of life as instantaneous, dramatic outbursts. But as we see, the greatest changes on Earth began with quiet, almost imperceptible steps. The conquest of land was precisely such a quiet revolution. Its engines were humble mats of moss and the finest films of microbes. They worked slowly, cell by cell, But the effect of their work was truly gigantic, planetary. Scientists studying this great transition are analyzing ancient spores preserved in rock strata. Some are nearly 1 billion years old. These spores have features similar to modern mosses, suggesting that land plants were already quite diverse by that time. Paleontologists are also studying isotopic signatures in ancient soils, which reveal chemical changes associated with the activity of the first plants. All this data contributes to a unified picture, a picture of gradual but steady colonization of land, beginning at the very edges of the continents and slowly moving inland. The spread of life across land also radically altered the process of erosion itself. Thanks to plants, whose rhizoids held the soil together, rivers were able to form more stable channels. This led to the emergence of entirely new landscape types. River deltas, wide floodplains, and meandering rivers became increasingly common as green cover conquered the land. These changes, in turn, created new habitats and triggered new feedback loops in which plants shaped the world around them, and the world shaped plants. Over time, these simple moss-like pioneers gave way to more complex forms: ferns, giant horsetails, and tree-like club mosses like lepidodendron. They grew taller, developed complex vascular systems for transporting water, and eventually formed the planet's first forests. But this entire green empire began with those tiny islands of life that once dared to leave the safety of the ocean. And the consequences of that step are still felt today. Every forest, every meadow, every blade of grass on this planet owes its existence to those humble early colonizers. They became a living bridge between the aquatic and terrestrial worlds, an experiment that, against all odds, was crowned with incredible success. The coastline is where it all began, and from there, the history of life began its triumphant march inland until once barren continents became living, breathing worlds. And while plants built their green empires on land, the oceans themselves were not standing still. They underwent their own monumental transformations, brimming with creatures even stranger and more complex than anything that had ever existed on Earth. Long before forests blanketed our planet and dinosaurs strode across Pangea, the oceans were already teeming with life. But this was not life as we know it today. No familiar fish scurrying among coral reefs or whales prowling the seas. These were far stranger, more ancient forms. Creatures whose body structure now seems utterly alien to us. Creatures that have not survived to this day, but once ruled the seas undisputed. When we try to peer into the depths of antiquity, to the very beginning of animal life on Earth, our imagination usually conjures up a simple picture. First, there were microbes, and then, an eternity later, the first fish appeared. But this is a vast simplification, leaving out an entire lost world. Between the era of single-celled organisms and the kingdom of fish, there existed an entire universe of amazing creatures that were born, flourished, and disappeared forever in oceans that no longer appear on the map. This incredible story begins in the Cambrian period, approximately 540 million years ago. At that moment, which in geology was only a blink of an eye, life on the planet exploded with unprecedented diversity. Scientists call this event the Cambrian explosion. In just a few tens of millions of years, the seas ceased to be a quiet realm of primitive, soft-bodied organisms. They became a seething cauldron filled with creatures with tough shells, sharp spines, the first eyes in history, and incredibly complex body structures. Here, on the ancient seafloor, we see the true kings of that era, the trilobites. Their segmented, armored bodies and complex compound eyes became the hallmark of the Cambrian. They crawled along the seafloor in countless numbers. Some were tiny, no bigger than a fingernail, while others grew to gigantic sizes, reaching 0.5 meter or more in length, making them the dominant force of their time. But trilobites were only part of this amazing marine ecosystem. Alongside them lived creatures that today would seem like aliens from another planet. For example, Anomalocaris, a predator without parallel in the modern world. It had enormous grasping appendages studded with spines, a round mouth reminiscent of a circular saw, and a flexible body perfectly adapted for swimming. Some of these hunters reached almost 2 meters in length, making them among the largest and most fearsome predators of their era. Imagine floating in the warm, shallow seas of the Cambrian, watching this alien hunter silently glide past, its body undulating in pursuit of a school of trilobites. Other life forms were no less bizarre. Opabinia had 5 stalked eyes and a long, flexible trunk ending in a claw. It used this tool to probe the seafloor in search of prey. Hallucigenia walked on stilt-thin legs, its back protected by sharp spines like a nightmarish porcupine. And Wiwaxia was covered in scales and long quills, resembling a living pincushion. All these incredible creatures have come down to us thanks to unique fossil finds, such as the Canadian Burgess Shale. These fossils reveal a whole world of evolutionary experiments, where nature tried out the most daring and bizarre forms. Some were successful, while others sank into oblivion, leaving no descendants. Fast forward several million years to the Ordovician period. Life in the oceans had become even more complex and diverse. The first reefs began to grow in the seas, but they were built not by corals, but by entirely different organisms, mostly sponges and algae. The seafloor was strewn with brachiopods, shelled animals similar to mollusks but unrelated. Above them towered entire forests of crinoids, or sea lilies. They waved their feathery arms on long stems attached to the seabed, filtering nutrients from the water. It was then that the first cephalopods appeared on the scene, the ancestors of modern squid and octopuses. Some of them possessed long, straight shells that could grow up to several meters long. These early cephalopods quickly became the top predators of their time, true masters of the oceans, which, until then, had been populated mainly by slow filter feeders and small-bottom dwellers. Imagine a giant living torpedo with a cone-shaped shell, darting through the water, tentacles protruding from its front end, ready to seize any prey. It was a sight completely unlike the flexible and graceful squid we know today. But it was these creatures that laid the foundation for the future success of their entire group. As time passed, one group of animals was replaced by another. By the Silurian and Devonian periods, the first jawed fish appeared in the oceans. The seas were swam by veritable armored tanks, placoderms covered in heavy bony plates. Dunkleosteus, one of the largest representatives of this group, reached almost 10 meters in length and possessed jaws so powerful that they could easily crush shells and bones. It was a true terror of the Devonian seas, one of the planet's first superpredators, hunting other fish. Along with placoderms, early sharks also inhabited the seas. They were smaller, but even then they were incredibly effective hunters. Bony fish also appeared, which would later give rise to the vast majority of modern fish. The Devonian period is not without reason called the Age of Fishes. The planet had never seen such an explosion of diversity in these creatures. Reefs grew taller and more complex, now built by true corals, and ocean life became increasingly dynamic and competitive. But even against this backdrop, strange and unfamiliar creatures still thrived. Eurypterids, sometimes called sea scorpions, prowled the shallows. Some were small, but others grew to monstrous sizes. Up to 2.5 meters long, their pincers clamped down on prey with relentless force. Trilobites still dominated the seafloor, though their golden age was drawing to a close. Ammonites, relatives of squid with spiral-shaped shells, became widespread. They left behind fossils that are now considered among the most beautiful ancient artifacts. The oceans continued to be a gigantic laboratory of evolution. Although many of the bizarre forms of the Cambrian period gradually disappeared, giving way to more robust and stable structures that have survived to this day, their role was invaluable. It was in these ancient seas that eyes first appeared, and hard shells and shells became the norm. It was then that the endless arms race between predators and their prey began. All the diversity of forms that arose in these early seas laid the foundation for all subsequent life on Earth. When we think of vanished seas like the ancient Tethys Ocean, we often imagine only slowly moving continents. But these waters harbored entire ecosystems, lost to time. Imagine reefs rising above the seafloor, taller than modern buildings, underwater forests of sea lilies swaying in the currents, gigantic swarms of trilobites scurrying in unison across the bottom, and enormous predators silently gliding through the dark depths. It was a living world, as rich and dramatic as any modern one, just completely unfamiliar to our eyes. But the seas weren't always a tranquil haven for life. Mass extinctions repeatedly wiped out significant portions of the Earth's marine life. The Ordovician Silurian extinction, which occurred approximately 440 million years ago, dealt a devastating blow to trilobite and brachiopod populations. The late Devonian extinction, which occurred approximately 375 million years ago, devastated reef systems and wiped out countless fish species. Each of these catastrophes completely transformed the oceans, clearing space for the emergence and flourishing of new groups of organisms. It was a never-ending cycle of boom and bust, driven by global climate change, fluctuations in sea level, and fluctuations in atmospheric chemistry. All of this was inextricably linked to the restless movement of continents and the cycles of supercontinent formation and breakup. What amazes scientists is the detail this ancient history has been preserved in fossils. The Burgess Shale in Canada, the Chengjiang Formation in China, and other unique sites offer us a glimpse into these ancient worlds, preserving in stone even the imprints of soft-bodied creatures that typically leave no trace. They reveal not only what early life looked like, but also how diverse, bizarre, and strange it was. Of course, the fossil record is incomplete, but what we've found is enough to imagine oceans teeming with life forms unlike anything we see today. If you could dive into these ancient seas, you'd feel like you were on another planet. Instead of schools of fish, you'd see swarms of slithering trilobites. Instead of dolphins and whales, you'd see giant cephalopods with straight shells swimming leisurely past. Instead of vibrant coral reefs, you'd see gigantic structures of sponges and algae. Predators would look like creatures from nightmares, and their prey would be no less bizarre. And yet, the very dynamics of life, hunting, finding shelter, feeding, reproducing, would be painfully familiar. Life was solving the same problems it faces today, it just used completely different tools. And it was from these oceans that the great march onto land began. Some fish developed primitive lungs and fleshy limb-like fins, allowing them to navigate shallow waters and then wet shores. Amphibians followed, then reptiles, mammals, and ultimately, us. But the oceans have always been the first stage, the testing ground where evolution conducted its boldest and most risky experiments. When we speak of ancient ocean dwellers, we speak of worlds as real as our own, worlds full of color, sound, and movement, even if their inhabitants seem alien and incomprehensible to us now. These were true pioneers who populated the seas long before the first forests appeared on land, strange precursors who paved the way for the emergence of all the animals we know today. And just as the oceans nurtured life, they were a mirror of Earth's climate. Warm periods, ice ages, greenhouse flares, all are forever imprinted in the chemistry of seawater and the remains of the creatures that inhabited it. And this brings us to the next question. What was the climate like in the era before Pangea, when our planet oscillated between icy crust and scorching hothouse, shaping the appearance of both oceans and land? When we imagine Earth's climate, it's tempting to think of it as stable. We're accustomed to the regular cycle of seasons and the familiar sky above. But in reality, our planet's climate has never been constant. It has undergone abrupt, dramatic changes, fluctuating between extremes that make our current state seem incredibly mild and calm. Before all the continents merged into the single supercontinent of Pangea, the planet experienced epochs of deep freeze. These were times when ice could cover the Earth almost to the equator. But there were also greenhouse periods, when tropical conditions extended to high latitudes and summer temperatures were far warmer than anything we can imagine. To understand the climate of the pre-Pangean era, we must imagine a world where the continents were scattered across the ocean, periodically gathering into earlier supercontinents like Rodinia or Nuna, and then drifting apart again. Imagine that our planet's climate, its entire weather, depended not on something invisible, but on something quite tangible. On the way, giant landmasses, the continents, were scattered across the ocean. It was their arrangement that controlled the great ocean currents, those rivers in the sea which were the primary drivers of global climate. When land masses huddled together at the equator, warm waters circulated very differently than when the continents drifted toward the cold poles. Add to this the birth and death of mountain ranges, the incessant fiery breath of volcanoes, and the constantly changing chemical cocktail of the atmosphere. And you get a picture of the Earth's ever-living, dynamic, and unpredictable climate machine. One of the most dramatic acts in this play unfolded approximately 720 to 635 million years ago. Immediately after the ancient supercontinent, Rodinia began to crack and break apart. This was a time scientists call the Put-Snowball Earth era. Geological evidence paints a striking picture. Glaciers, those gigantic rivers of ice, slid down from the mountains and reached as far as the equator, reaching sea level. Ice, like a shroud, covered virtually the entire surface of our planet. Let's travel into space and look at Earth at that time. Before you is not the familiar blue-green globe, but a blindingly white sphere, encased in a pole-to-pole shell of ice. Oceans are buried beneath kilometers of ice. Continents have vanished beneath ice sheets. Only in a few places, near hot volcanic vents, or beneath the thinnest, most transparent ice, where the dim light of the ancient sun could still penetrate, tiny pockets of liquid water remained. And yet, even in this icy hell, life did not give up. Microscopic organisms clung to existence, finding refuge near underwater volcanic vents or beneath the ice dome. What triggered this cosmic winter? One of the main reasons, most likely, was the breakup of Rodinia. When its fragments, the future continents, spread out and lined up along the equator, global changes began. Rocks in the warm, humid climate began to weather much faster, and this process, like a giant vacuum cleaner, began sucking carbon dioxide, the planet's main blanket, out of the atmosphere. Greenhouse gas concentrations dropped, and the Earth began to rapidly cool. The ice, like a giant mirror, reflected sunlight back into space, exacerbating the cooling. This process was unstoppable, but beneath the icy crust, the Earth's heart continued to beat. Volcanoes remained active. For millions of years, they spewed carbon dioxide into the atmosphere, its concentration gradually increasing. Eventually, the accumulated gas became so abundant that it triggered a powerful greenhouse effect. The icy shell cracked and melted, and the planet transformed from an icy desert into its opposite, a hothouse world. This swing between total cold and scorching heat demonstrates how fragile the climatic balance was. History shows that when continents came together, the climate became extreme. The interiors of supercontinents turned into parched deserts with monstrous temperature fluctuations, while the breakup of giant landmasses opened the way to warm, shallow seas with a mild, humid climate. During the existence of Nuna, about 1.5 billion years ago, the planet's weather was relatively equable, though significantly warmer than today. And during the birth of an even older supercontinent, Kenorland, Earth may have experienced its first great glaciations associated with the appearance of oxygen in the atmosphere. Each new supercontinent cycle triggered its own climatic rhythms, and the atmosphere played the leading role in this orchestra. For most of our planet's history, the carbon dioxide content in the air was 10 to 20 times higher than today. It was this dense greenhouse cocoon that warmed the Earth during the epochs when our sun was young and much weaker. But CO2 levels were never constant. They fluctuated constantly due to tectonic processes, Powerful volcanism pumped it into the atmosphere, while the weathering of rocks, conversely, removed it. It was a perpetual struggle between two elements, a system without any stable equilibrium. Periods of global warming could be truly scorching. During the Cambrian and Ordovician eras, warm ocean waters washed even the polar regions. Later, in the Devonian period, the first vast forests appeared on the planet. These green lungs began greedily absorbing carbon dioxide, causing a noticeable cooling. But before that, during the same period, tropical heat reigned virtually everywhere. And in the Carboniferous period, when plants took over the land, oxygen levels soared and carbon dioxide concentrations plummeted. This plunged the planet into another ice age, and giant glaciers encased the southern continent of Gondwana. These climate swings had a colossal impact on the living world. During the snowball Earth, life was on the brink of total annihilation. But as soon as the ice retreated, ecosystems exploded with an unprecedented display of diversity. This is when the famous Cambrian explosion occurred, filling the oceans with bizarre new animal forms. Hothouse worlds, in turn, created ideal conditions for life to thrive. Warm, shallow, food-rich seas became the cradles of giant coral reefs. Ice ages, on the other hand, brought death and destruction, wiping out entire ecosystems. But at the same time, they became a powerful impetus for evolution, forcing the survivors to adapt and become stronger. Climate extremes also altered the chemistry of the oceans themselves. During hot periods, the oceans often stratified like a cocktail. Warm water remained at the surface, while oxygen ceased to flow into the depths. This led to so-called anoxic events, when vast tracts of the seafloor turned into dead zones, killing all life. During glaciations, on the contrary, cold, oxygen-rich waters sank to the bottom, supporting life in the deepest reaches of the ocean. It was the balance between these two conditions that determined which life forms would thrive and which would disappear forever. If a time machine transported you to one of these eras, the difference would be stunning. In the world of Snowball Earth, you would arrive at the shore not to the sound of the surf, but to the ringing silence of an icy desert. The ocean would be frozen in a death grip. Sharp, dry winds would blow across the lifeless land, and the thin air would be almost devoid of carbon dioxide. Now let's move to a greenhouse world. Here, you would be enveloped in a stifling, humid heat. Monstrous tropical hurricanes would shake the sky, and the shores would be flooded by high sea levels. The damp land would be covered with dense forests or slippery mats of microbes, and the air itself would be heavy and saturated with moisture. Both of these conditions were part of the planet's natural rhythm. The hot summers of a hothouse world could last for millions of years, shaping entire ecosystems. Plants and animals that could tolerate the heat thrived, while others died out. For example, during the Devonian period, widespread warmth allowed giant reef systems to grow, but the subsequent cooling led to one of the greatest mass extinctions in the history of marine life. Extreme climates were never just scenery. They were the master director, writing the script for evolution. And yet, despite all these cataclysms, life survived, from microbes buried beneath thick ice to fish in boiling shallow seas. Organisms adapted, changed, and sometimes completely reborn. The climate of ancient Earth was unpredictable, unstable, sometimes harsh, sometimes generous, but it was always a force that changed everything. Reflecting on this turbulent history, our modern era seems unique. We live in a relatively stable climate, and our continents are positioned in a way that moderates any extremes. But the record of ancient Earth is a dire warning of how fragile this balance is. The arrangement of land and sea, the fiery pulses of volcanoes, the chemical composition of the atmosphere, all of these can tip the scales toward all-consuming ice or scorching fire. And as the climate shifted, so too did the forces hidden within the planet's depths. Volcanoes and earthquakes didn't simply reshape the world, they constantly introduced new variables into the complex climate system. They were a reminder that the Earth below was as restless as it was above. If there was one constant in the history of our planet, it was that it never stopped breathing fire. Continents moved slowly, oceans were born and died over millions of years. But it was volcanoes that provided the most vivid and formidable reminder of the planet's turbulent interior. Long before Pangea, Rodinia, or Nuna, the Earth's surface melted and reshaped under the onslaught of eruptions, lava flows, and eruptions of superheated gases. Fire has always been one of the planet's languages, a language of destruction and creation, but always key to the history of land, sea, and life itself. When we talk about volcanoes today, we imagine majestic yet solitary mountains like Fuji, Etna, or Kilimanjaro. But in ancient times, things were different. Volcanic activity was truly planetary in scale. Entire lava provinces existed, flooding territories the size of modern continents with basalt. Along zones where one tectonic plate subducted another, entire chains of volcanoes arose, spewing ash and gas into the sky. And in giant fissures where continents began to split apart, magma erupted to the surface and cooled, creating new crust. These processes never ceased, pulsating in time with the movement of plates and the cycles of supercontinents. Volcanoes weren't just landscape features, they were true drivers of climate and geology. Each eruption released carbon dioxide, sulfur dioxide, and water vapor into the atmosphere. CO2 warmed the planet. Sulfur dioxide, conversely, cooled it by reflecting sunlight, and water vapor fueled monstrous storms. Depending on the balance of these gases, volcanoes could tip the scales toward either a hothouse world or an ice age. And over the long eons that preceded Pangea, their influence was colossal. The great lava flows that accompanied the breakup of supercontinents like Rodinia around 750 million years ago left behind thick layers of basalt and forever altered the climate, releasing enormous volumes of greenhouse gases into the atmosphere. Some scientists even believe that it was this interplay between continental breakup, volcanism, and atmospheric chemistry that triggered the Snowball Earth era. Later, during the Devonian and Carboniferous periods, other massive eruptions further reshaped ecosystems and climate. The pattern is simple and inexorable. As the continents converged in a deadly embrace, chains of fire-breathing mountains rose along the seams. As they tore apart, entire seas of lava erupted from the fissures. Each key stage in the lives of the supercontinents was accompanied by a fiery symphony of volcanoes. But fire wasn't just a destroyer, it was also a great builder. Eruptions created new land, birthing islands from the sea's depths and expanding the boundaries of continents. Much of the early continental crust on our planet formed in such volcanic arcs, where magma rising from the depths cooled and crystallized, creating the foundations for future continents.